Great, so we're back for another video on important past paper questions you should know, and we're going to look at the types of questions that come up for probability. So as usual, I have a big PDF here. I think it's 133 pages in length, and I've put these kind of red stars beside the kind of important questions we should know. So what I'll be doing is I'll kind of pause the video in between scrolling through the document because it's so big rather than scrolling along as we move through. So anyways, we'll get straight into it. We won't waste time. We'll try and make good progress. So particularly for probability now, it's really important that when I get a question, say like this one here, when I get it set up, that you're giving it a go yourself, you know? So always be pausing the video, trying them, and then, you know, see, do you get the same solution as myself? Okay? So great. So let me get set up for this one. Okay, so what we're looking at here is these are very typical probability questions. So we've got to be aware of this formula here to learn it off by heart. The A union B, that looks like a V, but it's a union, is equal to the probability of A plus the probability of B, and then minus their intersection. So it's A intersect B. So that formula always works, okay? And we've got to know our difference as well too. We'll talk about this more in the video. So we have these kind of two Venn diagrams. Okay, so this is what's called mutually exclusive. So they mutually means they kind of agree to exclude one another, and then this is non. I'll call it ME. Okay, and this formula works for both of them. Obviously, when you're mutually exclusive, this guy will go to zero. Okay, because there is no intersection when they're this. Okay, so the formula still works in both scenarios. Okay, so that's fine. So back to this here. Find the probability of A. So you can see we've been given this, so you can just move this around here to get probability of A. I'll actually just sub in those straight away. So 0.9 equals what we're looking for, probability of A, plus probability of B, which is 0.6, and then plus take away this guy, which is 0.2. So then what's this here? It's 0.4, bring it over. You can see probability of A is pretty handy, 0.5. Okay, pretty important formula. Make sure you know it off by heart. So we'll see more of them as the video progresses. What do we got here? So these are a two-part type question. Right, so the probability of passing a driving test is 2/3. On a particular morning, 6 people take the test, okay? What is the probability that none of them pass the test? So the idea is that each of them taking the test, they're independent of one another. So like one person passing the test doesn't make like the others less likely to pass, kind of a thing. So we assume they're independent. So this is easy enough. Probability that none of the people pass the test. So that's just like 1/3 times 1/3 times 1/3. And you know what's going on here. It's basically 1/3 to the power of 6. So why are we multiplying? Because this person has to fail the test, and this person has to fail the test, and this person has to fail the test. So when we have the word "and" in our statement, it means multiply. So let me get my calculator for this. 1/3 to the power of 6. So that's working out as 1/729. Use a binomial distribution to find the probability that half of the people pass the test. Right, so what they're saying here is that exactly 3, this word exactly is really important for these, right? Exactly 3 people pass the test. And so yes, this is a binomial distribution. So the way you would write this for the examiner, you call it EX3. You'd spell it out in your exam for exactly 3. Probability of exactly 3 is this Bernoulli trial binomial distribution thing. So it's 6, choose 3. Then the probability of success is 2/3. And that's 3 successes. And then failure is 1/3, and that's 3. Okay, so we should be all pretty comfortable with this binomial trial formula. Okay, so I'll type that into calculator. So 6 choose 3 times 2/3 power 3 and 1/3 power 3. So that's working out as 160/729. Okay, cool. So let's move along. So I'll clear this away. Okay, so they're done. So straight after this, we got another kind of a two-part question. And then that covers us for that question. Okay, so let me snip this and then obviously be pausing the video, giving it a go. Right, Green Schools committee of 4 people is to be selected from 3 boys and 4 girls. How many different committees can be formed? Right, so you've really got 7 people here, and you have to choose 4 of them. So it's pretty straightforward. 7 choose 4, right? Hopefully that makes sense to people. You're choosing 4 people from a total of 7 people, and that's 35. Okay. How many different committees can be formed if there are more girls than boys? Okay, so you want the girl majority here. So you kind of write this out what this looks like. So this, if how many total girls are there here? So there's 4 girls. So one committee is 4G, 0 boys. Or there's the committee where there's 3 girls and 1 boy. And it's not the 2 girls, 2 boys one because then that's not a majority, okay? So it's both of these. So it's either this scenario or it's this scenario. So or kind of means add as well, so we should know that. So how many different committees can be formed if they're okay? So if we want 4 of the girls, what that looks like is 4 choose 4, right? And we want 0 of the boys, so that's 3 choose 0, like such. So that's the first scenario. Or we can have where we choose 3 of the girls, so there's 4 choose 3, and then we choose 1 of the boys, so then that's 3 out of the 3 boys choose 1. Okay, so hopefully that makes sense to people. You can do some of this stuff in your head. You should know that 3 choose 0 is 1, 4 choose 4 is 1, so this number is really just 1 here. And you should know 4 choose 3, that's 4, and then 3 choose 1 is 3, so it's like 12, so 13. Now you can, if you don't know that, you can just type it into your calculator. Okay, so there's 13 committees where there are girl majority. So hopefully that makes sense there. So the reason we multiply them is because this committee here is 4 girls and 0 boys, or there's the scenario where we have 3 girls and 1 boy. Okay, so that's why there's multiplication and adding where there are. Okay, so hopefully that made sense to people. So what I'm going to do now is I'm going to kind of pause the video and roll along to our next video because it's a pretty big document, you know. Okay, so I've skipped along to our next question here in the document. For people interested, this is from 2025 mock paper 2. So we have someone that has, they're kind of seems to be a goalkeeper, and they have some machine that takes shots on them. Okay, and as you can see here, for the next 7 days, uses the machine for the next 7 days and finds that the probability of her stopping a ball is 45%. Okay, so this should sound like a bit like a Bernoulli trial T. Uses with the machine 12 times. Okay, what is the probability that she will stop the ball from entering the goal exactly 4 times? So the word exactly is very important here, right? So hopefully you realize this is a Bernoulli trial. These are very important. You can write probability of exactly 5. So out of the 12, we choose 5 of them. And the probability of success here, we want to, what was it, stop the ball. And the chance of stopping the ball is 0.45. So we want 5 of them. And then 0.55 to the 7 here is for our failure. And then we want 7 fails, okay? So that works out as, we'll choose 5 times 0.45 to the 5 and 0.55 to the 7. So you've got to be pretty comfortable with this kind of Bernoulli trial. So give it as a percentage. So I write down to 4 decimal places first of all. 4 or 5, and then that as a percentage is 22.45%. Okay, so yeah, we've got to be pretty comfortable with those exactly scenarios. So another interesting one here in part C. Again, uses the machine 12 times, but what is the probability that she will stop the ball from entering at most 3 times? So definitely pause the video, give that a go. So at most 3 times is defined as this. It's the probability that you let in that she will stop, that she will stop the ball from entering at most 3 times. So it's the probability of exactly 0. Okay, exactly 0 stops. You could write it like this. Or plus the probability of exactly one stop plus the probability of exactly two stops, and then it's plus the probability of exactly three stops. Hopefully that makes sense to people. So, because you have to add up all your exactly scenarios, at most three times is zero stops plus the one stop scenario, the exactly two stop scenario, the exactly three. So there's a bit of work in calculating all these. Um, so we gotta I'll write it out maybe up here. So exactly zero stops. So that's like 12 choose 0, 0.45 to the 0, 0.55. So basically let's in all 12 of the shots, okay? And then you add that to, or the scenario where there's exactly one. So that's like 12 choose 1. So hopefully you can see the pattern here. This is just what it looks like if you stop exactly one shot. And this is 11. And then add that to stopping exactly 2. To the 2. And then this is a 10. And then the last one, then this is stopping exactly 3 shots. Okay, a really important type of question that kind of thing comes up a lot in past papers. So um, you've seen it now. So I'll type that, I'll pause the video and obviously type that in there. It's a bit meaty to type in while the video is rolling. Okay, so I typed all that in there and I got 0.13, 4, and 5. And so then as a percentage again, it's 13.45% chance of stopping the ball at most three times. Okay, so really important example, and obviously, kind of practice a few of them in your spare time and when you're going through similar documents like this. But those Bernoulli try ones, they're pretty, they get asked a lot, so you want to be on top of them. Okay, so again, I'm going to pause the video and just scroll along to the next question. Okay, so we're at 2024's paper 2 here. So I got an expected value question, and then I've got a mutually exclusive question down here. So both of these are interesting. So let me zoom in and take a snip of this to get it set up. And obviously try it yourself. Pause the video. Okay, so really important for us, expected value, we usually write it like this, e of x, and we get it by multiplying, say, x's value multiplied by the probability of getting that value. Okay, that's kind of the idea. And then we sum all those together. So big E like that with you've seen that symbol before. I'll draw it a bit better here. So that means sum. Okay. So the table below shows the prizes in euro that a player can win in a game, as well as the probability of winning each prize. Cool, typical table. The player wins at most one prize each time at the play. Some of the prizes are given in terms of X. Indeed, they are. Okay, so it costs €10 to play the game once. The game is fair. That is the expected value, yeah, is equal to the cost to play. Work out the value of X, right? So the idea is here, you win 0. So we'll write it like this, E of X equals, so we win €0, 0.3 of the time, plus, that's what the big E thing means here, plus we win €2, 40% of the time, plus X minus 10, we win that much money, 28% of the time, 0.28, and then finally plus, we win probably this big prize of X, only 2% of the time, like such. Now we're told that the game is fair and it costs €10 to play, so then the cost to play, the E of X, and the expected value should be the same, and so then this will be 10. And look what we got there. We've got one equation, one unknown, so you can kind of move this around, so it should be easy to do. And that's a 0. This is 0.8 here. Then this is plus 0.28x, and then this is minus 2.8. That thing there. And then this is a plus x times 0.02. Okay, so what we'll do is we'll take those away, so that leaves minus 2, so then you got the number 8 equals this plus this, so they add together quite nice. I'm getting 0.3x, I think. And then x is equal to 8 divided by 0.3. It's interesting to see how that goes in. Yeah, so x is working out to be an awkward number there. I'm getting 6.7 euros. So let me see if I done that calculation correct. Oh yeah, that's my bad there. So I knew there was something suspicious when I was getting a funny number like this. So yeah, so basically when you get the zero point 0.8, subtract minus 2.8, you get minus 2 this side, it comes over to be a plus 2. So this is a 12. And of course then 0 0.3 divided by 12 is 40 euros. And that seems and sounds a bit better, okay? So that's a typical expected value question there. Okay, so that has us covered for that type of question. So mutually exclusive, I mentioned this earlier on in the video. So what mutually exclusive looks like. Um, it has no, you draw the diagram of it. So the word mutually exclusive means they agree to not intersect. So then that's 0, there's no intersection. And their union is just their probabilities added together. Okay, so that's 0.5. Right? And again, this formula always works for them, that the A union B equals the probability of A plus the probability of E, take away the intersection. And in here, when you're mutually exclusive, the intersection is 0, okay? So it's just them added together. Great, hopefully people are okay with that. So really important stuff. What do we got down here? Another interesting event. C and D are two other events with the universal set. So let's have a look at this. Let me get it set up. Okie doke. So C and D are two other events, right? And as we said, universal set U. So that just means they're kind of inside a box. So find the maximum value of this thing, right? So we need to understand a few things here, and they explain kind of what that thing is, but technically they shouldn't be explaining it to us. We should just know. So what we'll suspect first of all is that there is an intersection. There probably is. So you just draw the typical Venn diagram, the Z and the D. Right. What we don't know here is the intersection. So at junior cert you would have learned best thing to do here is to call the intersection X if you don't know it. And then we know then that all of C is 0.5. So hopefully you can agree that this out here is that. So because all of C is 0.5, this part has to be 0.5 minus X, because when you add them back together, then you get 0.5. And the same logic out here. This is 0.7 minus X. Okay. And then it says, what is the maximum value, okay, of C union D complement or not? That means complement and not. Okay, so just basically think about that as in not. So what that means is, first of all, this here that let me get a good color for this. This is what I'm shading in here in orange. All of that in orange is known as probability of C union D, right? So C union D not is everything that I haven't shaded in there in orange. So it's basically this region out here. Okay. So the shading is very helpful when you're trying to make sense of what a question is asking for. So we're really asking for what the value out there is. Okay. So we're going to put something out here. We're going to call it Y. Okay. So what can we write down here? Well, we can add them all together. We know they have to add up to 1. So if we add them together, you'll see you get something like 1.2 minus x plus x minus x. So that'll be a minus x. Add the y on the outside, and then that's all equal to 1. What you'll do then is you can bring the 1 over here, these guys over here. So you get something like x minus y equals 0.2. Okay, so this is what I've circled. Two unknowns, one equation. You cannot find x and y here, but you can maximize it though. So think about it. We're trying to maximize y's value. Okay, so how do we make y as big as it can be? So it'll be more logical to get y on its own here. So y will be equal to x minus 0.2, right? So to make y as big as possible, you want to make x as big as it can be. Hopefully that makes sense to people. If you want to make y big, you make x as big as it can be. Now you come to the diagram and you ask, how big can x get? So the idea is you couldn't have x as 0.6, for example, because if x was 0.6, then you'd be getting a negative out here, which you couldn't have, okay? The biggest x could be is 0.5, because if you're 0.5 here, then you get a 0 here, which would be okay. So to make y big, you make x as big as possible. So you set x to be equal to 0.5, and when that's the case, that's as big as x can be, y will equal 0.3. You go 0.5 minus 0.2. Okay, so that's the max it could ever have. So it's an interesting question that, as I said, we don't have enough information to work out what x and y are. They can vary in value because we don't have enough information. But what we can do is we can, if we want to make y big, we can study what we can do to x to make y as big as possible. And that's what this question was about. So they come up in past papers, and now you've seen how that kind of question goes. Okay, so hopefully good learning for people from that. Right, I'll clear this away. Okay, so that's out of the way now. So we have a simple question here now. Obviously, pause the video, have a think about it, and what would you write down here for an answer to this? So the idea is one of the events, E, is that it will rain tomorrow morning, and F is the event that you'll wear a coat going outside tomorrow morning. Explain why it would not be reasonable to assume they are independent. Right, so we need to understand what independent means. It means that if E occurs, it does not change F occurring's probability. Okay? Hopefully that made sense to people. And it wouldn't be reasonable in this question. If E does occur, okay, as in it does rain tomorrow, that would make F more likely. We're more likely to wear a coat if it's rained, okay? So that is why they're not independent. They're actually dependent on one another. If E occurs, F is more likely to occur. And if E does not occur, as in it doesn't rain, then F is also less likely to occur. Because, if it doesn't rain, you won't need the coat as much. Okay, so hopefully that makes sense to one another, to people who are watching. So you would kind of put that into words there, that, they would be actually dependent, because if it rains tomorrow, you're more likely to bring a coat, and you get sort of full marks for that. Okay. Cool. Right, so I'm gonna scroll along now, pause the video and scroll along. Okay, so I scrolled along here to 2024, and we have a question on something to do with hotels. Hotel customers, during their most recent stay, 1/5 of the customers use the pool. Okay, straightforward stuff. Sounds like you can sort of get the pattern of these. These sound like the Bernoulli trials, 6 customers are picked at random, so it is a Bernoulli trial. And there you go, there's your buzzword, exactly 2. Okay, so you should just know how to do this now. Probability of exactly 2. It's 6, choose 2. And then it's the probability of success, which is a 5th. That's, using the pool. And that's power 2. And then 4/5 is the failure. And that's the power 4. Okay, so I'll type that into the calculator. 6, choose 2. Times 1/5 squared times 4/5 power 4. So again, it's nicer, unless they tell you write them as a decimal, it's actually nicer write them as a fraction like this. Okay, I wouldn't be writing that down as a decimal. That's the way to present your answer. Okay, I'll clear this away. Okay, so I cleared that away and I scroll down. So there's actually a part 2 to this question. You can see that this was hinted at, that there was a part 1 and a part 2. So, and I put 3 stars beside this one because this is a really important one. Okay. So these come up. They're a pretty liked question. So you need to know how to do them. So obviously pause the video, give it a go. So, right, what do we got? We've got talking about none of them using the pool, okay? And we're trying to work out how big the number of customers we sample are, okay? So the idea is here, we need to think about what's the probability of n customers not using the pool, okay? So we know that a 5th is the probability of using the pool, so then 4/5 is the none of them not using the pool. So the idea is here, if you had, say, 6 of them that didn't use the pool, right, it's 4/5 the power of 6, right? If you have n of them that don't use the pool, it's 4/5 of the n, okay? And we can see this as well too. I'll just highlight this with the Bernoulli trial. So let's say we done probability of exactly 0 of the 6 using it. So exactly 0. So then it's 6 choose 0. Remember, 1/5 is the probability using it, so that's the power of 0, and then it's 4/5 to the 6. Now, why does this just work out as 4/5 to 6? Because 6 choose 0 you should know is 1. Anything to the power of 0 is 1, so this is 1 times 1 times 6, or 4/5 to the power of 6. So realistically, these don't come into it, and it's just 4/5 to the 6. And so if you had exactly 0 for n customers, it's 4/5 of the n. So hopefully that makes sense. Now we're asked the probability that none of them use the pool correct to 4 decimal places is this number. Work out the value of n. Okay. So we just set this here equal something like this, 0.47. And we have to get the n. And so to get the n here, you got to use logs, okay? Because the unknown you're looking for is in the power. So the way logs work, the whole point of logs is to get the power on its own. So the power will be on its own. The base here is 4/5, so that will be the base of your log. And then that just leaves room for this other guy here. So let's work out what n is. So this question is actually pretty easy. It's not necessarily the trickier one I thought it would be, but it's still important to see it done. So n there is working out as 24.02. So what I'd say there, that's so close to 24, you would just put down the answer as 24. But sometimes, I think maybe they're usually a bit more specific on when the probability goes above or below this, and you'd have to test whether or not it's 24 or 25, But because it's so close there and they're not very specific in the question, I'd be happy with this being 24. Okay, we'll see a more complicated version of that anyways later in the video. Great, I'll clear this away. Okay, so we're back. So we've seen that I put kind of 4 marks beside these 4 questions here. So this is kind of marbles in a bag, something in a bag, with different colors. So yeah, we'll get straight into this. So I'll be able to kind of probably write these in the screen because there's a few of them. 5 reds, 4 blue, 6 white marbles are in this bag. Marbles are drawn out and not replaced. That's very important, okay? So because they're not replaced, what happens on the draw before changes the probability on the next draw. Okay, hopefully that makes sense to people. Right, find the probability that the first marble drawn is not blue. Pretty straightforward. What are not blue in this bag? There are 5 red, 6 white, so it's really 11 over, how many is in the bag? 5, 9, 15. Yeah, easy stuff. The first red marble drawn is the third marble. Right, so what that means is in 2 draws you did not get a red marble, okay? So in the first draw here, we need to not draw red marbles. So there's 10 not red marbles here, so 10 over 15. Okay, and we need to also draw a not red marble again. So now there's 9 of them left, and there's a 14 in the bag total. And now we have to draw a red marble on our third draw, okay? So then there's 5 red marbles in the bag, and there's 13 marbles overall left in the bag. So hopefully that makes sense to people. The reason we're multiplying here as well is because we needed to get no red marble, and we needed to get no red marble, and then we get a red marble, okay? Hopefully that makes sense. So what's part 3 here? Let me scroll down a bit. So the first 3 marbles drawn are all different colors. All different colors, right? So there's a few different ways to do that one if you think about it. The first 3 marbles drawn are all different colors. So you could do this where it's like you draw, say, the red one first, then the blue one, then the white one. Or, so it's basically you just want to find how many different ways you can reorder this here. So how many different ways you can reorder 3 letters. That will be one way of doing this. And we'll walk you through maybe another way afterwards. So I'll follow through with this method here. It will take a few calculations and we might see a pattern. So red, blue, white marbles. Then the other one would be if we've got, and I'll show, what's the best way to kind of iterate through these? So yeah, if we want to know how many different ways there are to reorder these 3 letters, you can use 3 boxes like this. So it's 3 by 2 by 1. So there's going to be 6, because there's 3 options, red, blue, or white for the first letter slot. Then there's just 2 letters left, and then there's 1. So there's 6 different ways I should be able to reorder this. Now let's see, can I write them out by hand? Red, blue, white. Red, white, blue. I'll put white first. So B or W or B. And then I'll put the B here, and then I'll go W or, and I'll put the B here, and I'll go R W. Okay, so there's the 6 scenarios. And then you're going to see probably something appear here now when I multiply this out. It's usually how it goes. So pulling a red marble first is 5 over 15. Then a blue marble is 4 over 14. And then a white marble is 6 over 13, right? And these are all different scenarios, so it can be this or this or this. So these are added together. So that's this first scenario here, or BW. So if I do or WB, you're going to see something interesting up here, I imagine. So red again would be 5 over 15 times the white marble, which is 6 over 14, and then the blue marble, which is 4 over 13. Now, what you'll notice if I went and done all these out by hand is you'll notice that the bottom is always the same. It's always 15, 14 by 13. And the top is always just these three numbers like 5, 4, and 6 just reordered, okay? So you're really, hopefully you can see, you're just adding together they are the exact same number every time, if that makes sense. If I multiply this out, I get the same number as this up here. So all you have to do here is really work out one of the scenarios and then multiply it by 6. Okay, hopefully that makes sense to people. So I'll get an answer for that. So 6 times 5 over 15 multiplied by 6 over 14 multiplied by 4 over 13. But it is a tough question. But it's hopefully useful to people now to have seen something like this as an answer. So that equals 24 over 91, okay? So I'll clear this away and see if there's any other way I can kind of walk you through this and how to come up with it. Yeah, I had to think about that. There's not really many other ways to do it. It's just kind of, if you're ever seeing something like this, it's good to list it out by hand like this and kind of do out the calculation like that. And if you say this here is really useful to work out how many of these you're looking for. It's like I knew I needed to get 6 of them, so I kept going until I got 6. That'd be like I wouldn't be trying to get a 7th one here because there isn't another way of reordering these. So observing this thing here with the box is pretty important. Now there'll be more questions like this later on in the video where we're working out how many scenarios there are for rearranging something, So we get onto that soon. At least, let's see, can I zoom out here and get all this into the page? No, I can. At least one blue marble is drawn among the first 4 marbles, right? At least one. Okay, so this is a bit of a buzzword in probability. We need to know how to deal with at least one, okay? At least one, when you're drawing 4 marbles, is the same as getting probability of exactly 1 drawn, plus or probability of exactly 2, plus the probability of exactly 3 blue marbles. Remember, we're drawing 4 marbles, so then there's the last scenario, which is the probability that we drew exactly 4 blue marbles, okay? And because there is 4 blue marbles, so that works. Now that's going to take a whole lot of working out, right? So there's an easy way to do at least one. There's only one scenario missing from this, and it's the probability of getting exactly 0 blue marbles. All of these are the 5 possible scenarios, right? Okay, for drawing 4 marbles. You get exactly 0 blue, you get exactly 1 blue, exactly 2 blues, exactly 3, or exactly 4. So, because our answer is this here in blue, there's a quicker way to add up all of that. Because as I said, all 5 of these are all possible scenarios. They all add up to 1, right? So to get this thing that we're after here, we should all know this pretty quick routine for getting at least 1. At least 1 is go 1 minus the probability of none. Okay? That's the quick way of getting a probability of at least 1. I'll spell it out, the word 1 as well. Okay, so that's something for your flashcards if you didn't know that. At least 1 is quickly gotten from going 1 minus none. And none means exactly 0 in this question. That's drawing exactly 0 blue marbles, okay? So you only need to work out one scenario and take it away from one and you get probability of at least 1. So let's do this here. So let's work it out. So what is the probability? I'll actually leave that there. And I'll just drop down a line here and work it out. So then this is 1 minus the probability of drawing no blue marbles. So at least 1 blue marble is drawn among the first 4 marbles. Yeah, so if you don't You draw, does it say how many marbles were drawn? Doesn't specifically, so I'd say this is exactly one. Does it say how many marbles are drawn out? The wording's a bit funny, so let me think about this before I write it out. Yeah, so my reading of that is we're drawing 4 marbles, if that makes sense. So to get exactly 0 blues in drawing 4 marbles, it looks like this. So draw no blue, so that means the 5 and the 6, 5 red and the 6 white, so that's 11 over 15. Then we want to draw not another blue, so there's 10 non-blues out of the 14. Then it's 9 over 13, and then it's 8 over 12. Okay, that there, what I've written in pink, is the probability of getting exactly 0 blue when you draw the first 4 marbles, right? Yeah, that looks good. And then we take that away from 1, so let me type that into calculator now. 11 by 10 by 9 by 8, 15 by 14 by 13 by 12. Okay, so I'm getting that to work out as 69 over 91. So a little bit of a tough question, that, but very exam grade stuff, okay? So hopefully that made sense to people, this particularly down here. And then making the flashcard on probability of at least 1 is quickly got from going 1 minus none, okay? Right, I'll clear this away. Okay, so I've kind of scrolled through the document, see where I've got the next marks. So we're making decent progress here. So this is a deferred exam in 24. So A, B, C, D, E, and F are 6 events, right? And we just talk about 2 of the events here. A and B are independent. You're told their probabilities here, and you're told to find their intersection. Right, so we're meant to know something pretty important here. That if 2 events are independent, this formula works. Okay, I'm going to write down a formula here. And if you didn't know this formula, you want to make a good clear note on it in your flashcards and in your notes. Probability of A multiplied by the probability of B equals the intersection. This formula is only valid when they are independent. Okay, so you'd put a big note beside that. You cannot always use that formula. That formula will only work when they're independent. So the intersection in this question here will just be as simple as multiplying the 2 probabilities together. Okay, and that works out as whatever, 0.06. Right, yeah, we'll talk more about independence later on in a few other questions, okay? So, but for now, that formula there is pretty important. Okay, we're told about 2 other events now, C and D, and we're given their intersection, and we're told to find their union. So this is that formula we've already used today. Let me get that written in right. So it's where C union D equals the 2 guys added together, and then take away their intersection, C intersect D. And we have all the guys there, so that's straightforward enough. So that's like 0.4 plus 0.5, take away 0.08. So that works out as something like what? 0.82 in my head, okay? Grand, you can use your calculator to confirm that. Okay, so clear some of that away. All right, we're told about E and F. Now F has an X in it, okay, so let's zoom in on this. This could be interesting. So F has an X in it, and then we're given the intersection that also has an X in it. So we could actually do a diagram of this because they're 2 events if we wanted. But we're given here the given probability, okay? So we've got, yeah, so make sure you're not someone who's silly and thinks that that's E less F, which is a completely different thing. That means E without F. That's not what this means. This means probability of E given F. The vertical line means given. Now we need to know the given probability formula. So probability of E given F, it's fairly straightforward, remember. It's something over something. It's always the intersection of the 2 things on top divided by the last thing mentioned. Now what's the last thing mentioned here? It's F, so we divide it by the probability of F. So it's really easy to remember the given probability formula, okay? So E given F is the intersection on top divided by the last thing mentioned, which is F. Okay, so we can probably sub in here. So we have a quarter equals the intersection, which is X, over, what's this here, probability of F. So this is X plus 0.4. So this is manageable now because this is one equation, one unknown. So we can sort of cross multiply here. And we'll get X plus 0.4 equals 4x. Bring this x over and we got 0.4 equals 3x. And so x is looking like it's going to work out as a fraction anyways. 0.4 divided by 3, so I'm getting 2 over 15 there for x, okay? And yeah, it says x is a real number, so it's not supposed to work out as anything super neat. Okay, that seems reasonable, so I'll clear this away and go on to the next question. Okay, so we're back. So this seems to be this deferred paper again, but we're on to question 6 in it now. So it's talking about a 7-letter code, maybe for a safe or something, you know, a password. And it uses the letters going from A to G. Each letter is used exactly once in the code. So the code has 7. It does have 7 letters, okay? How many such codes are possible? Now, this is where the order of the codes matter, okay? So, for example, A, B, C, if we were just ordering them like this, is different to BAC, okay? So when the order matters, it's what's called a permutation. When the order doesn't matter, it's called a combination, okay? So they would be like the same combination. They're not something different. But for permutations where the order matters, they are different, different codes, different options. So when you want to do permutations, you just use the box method, okay? You just use boxes. So you put in an empty box for each of your 7 slots. Like this. So permutations, where the order matters, you use the boxes. How many different possible letters are there for the first box? There's 7. You've used up one of your letters. Then there's 6, 5, 4, 3, 2, 1. Okay? So in scenarios like this, where the order matters of the way you lay these guys out, you use a permutation like this. Now we should all know that that's 7 factorial, because when you multiply from 7 down to 1, the boxes multiply together, obviously. So 7 factorial in our calculator. So that says there's 5040, and it's got units of codes, okay? So that many codes. Right. So then they have a funny thing down here. So this kind of question comes up. This gets repeated quite a bit, where they like make you like put the vowels together, or they make you put something first in the word, okay? So these are important. They come up in past papers. And how many of these codes are the 2 letters A and E together? Right, we need to visualize this. So let's get back our 7 empty boxes, okay? What's that? 5, 6, 7. Now the vowels are going to be together, right? So they're kind of making up their own box like this, if that makes sense. So this is going to be the scenario where the vowels occur together, but in the first 2 letters, right? So then there's the question of, this is a specific scenario we're going to do to help people understand this. So let's say the vowels occur together in the first 2 letters of this code. Now there's a question of, who do we put first, A or E or E or A? So realistically, there's 2 options for who we put first, and then there's 1 option then for once we put one of the vowels first, okay? So then we've got to fill in the rest of the code. So there's 5 other letters, so then there's 5 options for there. You've used 1, so now there's just 4 options. 3, 2, 1. Now this is not the final answer. This is a very specific scenario where the 2 vowels occur together. Yes, that's what the green box is about, but they occur together as the first 2 letters of the code. There is also this scenario. Okay, so or, we could write down an or here. I'll put a plus, or, let me get you another 7 boxes. 4, 5, 6, 7. The vowels could occur together here as the second and the third letter. So again, we're going filling in our vowels here. Who goes first? Well, we have 2 options, 2 of them, and then 1 of them. Okay, so let's then fill in our non-vowels. So then this is 5 options here. Then this is 4, 3, 2, 1. So hopefully that makes sense to people. Now study it. It's still the same numbers multiplying together. Can you see this? It's 2 by 1 by 5 factorial. This is 2 by 1 by 5 factorial. So when I work out one of these, I'm just adding it to the same number again. So hopefully you can realize the question now is really just how many places does this green box move into? So let me get a good color for this. Maybe I'll use pink. So it can occur there. It can occur there. The vowels could occur there, or they could occur here, or they could occur here, or they could occur at the very end. So how many different places can the vowels move? So let's add it up. So they could be here in this, 1, or they could be here in this green box, 2, or here, 3, 4, 5, and 6. So there's 6 different things that I will be adding together with this black plus. So whatever this works out to be here, and let me type it into calculator, 2 by 1, by 5, by 4, by 3, by 2, by 1. I'm getting 240 codes. Because the vowels can move into 6, there's 6 different ways you can put the vowels together. There's really 6 of these, okay? We'd go 240 plus the 240 for this one, and then we'd add on another 240, another 240, another 240. You do it 6 times. So hopefully that makes sense to people. So 240 by 6, so there's 1440 ways. Okay, so hopefully that makes sense to people. Just to kind of calm people down as well, I'll do just another one maybe where the vowels occur in this next box here, where they're the third and the fourth number. Okay, so I'll just do this just in case anyone was super confused by that, but I'm sure some people got it pretty well there. Pretty important question this. So we're saying the vowels occur in this pink box where my red arrow is pointing. So that's them occurring here. So we put the vowels in there, 2 and 1, and then you put the non-vowels out here, 5, 4, 3, 2, 1. You see it's the same numbers, and so that again is going to be 240. And you can see then we move the boxes in like here, here, and here. And there's 6 in total, okay? Great, so hopefully that makes sense to people, and the answer, of course, was 1440, as we said before. Okay, pretty important question that, okay? So the video is on, what's it on there, 46 minutes. And this is a pretty important question when you see me doing the 3 stars like this, it's pretty important. And this is one of those interesting Bernoulli trials one, and then we also have another nice at least 2 here. We already showed you how to do the at least once before, now we're going to show you how to do at least 2. And then this is an interesting one where the 4th tackle is the first one that's missed, that kind of thing, you know. It's like if you're an archer, his first score is on his 7th attempt. We need to see how to do that, you know. And I'll do that in the next part of the video. We're not going to, we'll break this up into smaller chunks. So we'll end the video here and we'll see you in the next part. Thanks for watching. Okay, so we're back for the part 2 of working through important past paper questions on the topic of probability that you should know. And we said we pick up from here on this type of question here. So this is going to be a Bernoulli trial. So let's have a look at the very first one, and then we look at the part 2. So what do we have? So there's some rugby team, and they usually miss 8% of their tackles that they attempt, right? Use this fact to answer these next 2 parts, okay? Assume that all tackles are independent. So what does that mean? So that means that if you say do not miss a tackle, it doesn't change the probability of what happens in the next tackle, whether you get it or you don't, okay? So that means it's not like, oh, you made a tackle, so you're more likely to make the next tackle, you know? Or like you missed a tackle, so your confidence is down, so you're actually, you know, you're more likely to miss again in the next time. So that's not, when we say independent here, it's like, you know, they're pretty cool-headed, so they're always an 8% constant every tackle. Okay, great. So, because, you know, it's important, sometimes they make you explain those kind of things. Find the probability that the 4th tackle in the game is the first one that is missed, right? So if 8% is a miss, right, that is what we'll call a success. So it's like we want our first success to be on our 4th attempt, right? So if we want our first success on our 4th attempt, that means we've had 3 fails before, okay? So 3 fails in a row looks like this. It's 0.92 to the power of 3. Okay, so it's a little confusing because miss and fail are a bit different here. So, so hopefully that makes sense to people. We want to have 3 not missed tackles first of all, and then we want to have our very first miss, which will look like this here. So it's nice and simple. It's 0.08. Okay. So it's in a very specific order. There's no other way you can do this. You know, it's just you do not miss, do not miss, do not miss, and then you miss. Okay. It's not like they can be jumbled around. They're actually in a very specific order, you know. Okay. So hopefully people are okay with that. So that was particularly easy. There'll hopefully be another one of them where it's like, like their third success is on their seventh attempt, something like that. Okay, and we'll do a question like that when it comes up, but this was a little bit too easy, that one. Okay, anyways, I'll move on for the sake of time. So this is a really important type of question. So obviously pause the video, give this a go, remembering that what was it? It was 0.08 was the miss chance. That's the chance of missing. So find the probability that the team misses at least 2 of the first 20 tackles. Now, you'd never ever do this out by hand. At least 2, right, is the probability of exactly 2, exactly 3, exactly 4, all the way up to exactly 20. And if you've watched it in the part 1, it takes ages to just do one exactly out. So the quick way of doing this is you go 1 minus the 2 scenarios at least 2 doesn't include. So you take away the exactly 0 EX 0 scenario and the exactly 1 scenario. Okay? Because if you think about it, if you take away, these are the only 2 scenarios that aren't included when you're working out the probability of doing something at least twice. Okay? So you go 1 minus the exactly 0 times and the exactly 1 time. Okay? Right, hopefully that makes sense to people. So then we go back. I never worked the number out there actually the last time. Let me write that down for people who actually done it. What was it? It was like 1.92 cubed times 0.08. Because we want to keep the answers going. To the power of 3 divided by 0.08. Yeah, so maybe a neat way to write that would be 4 decimal places. So 0, 6, 2, 3 will do on that, okay? So there's only like 6% chance on that previous question. Right, so I'll clear that away. So we want to get exactly 0 misses. So that's our Bernoulli trial. So what this is here, in 20 attempts, we want 0 successes, right? And we class a success as a miss, right? So this is exactly 0 misses. So power 0 and then 0.92 power 20. And we add that to getting exactly 1 miss, and that's 20 choose 1 times 0.08 to the 1 times 0.92 to the 19. So it's a really important question, this kind of thing, you want to get. It's easier when you're getting at least once, because then you just go 1 minus the exactly 0 scenario, but at least twice is interesting because you have to take away not only the exactly 0, you have to take away the exactly once as well. Okay, so let me type that into calculator. That might take a second, so I'll pause the video. Okay, so I typed all that into my calculator there, took 1 away from it, so I got 0.4831. So what you'd want to do there is, it's nice to have our numbers equal to something, so what you would say, if you can, write it out like this. So this is probability of at least, this is probability of miss at least 2 tackles. Okay, out of 20, you could write it out there, but it's a little bit messy. So because the description of what this thing is quite long, you'd nearly not have to say it. But for yourself and your own workings, it's nice to have things equal to stuff, not just loose numbers like this up here. Okay, right, we'll move on from that. We won't delay. Lots to cover. Okay, so another question here. You see an expected value mentioned there, so it looks like an expected value question when you see values and then the probability of getting that value. So everyone should pause the video, give it a go. All right, let's see what they're saying here. At a particular stage of the game, this rugby team will score 7, 5, or 0 points, okay? The probabilities of each are X, Y, Z, and they're real numbers. The probability of getting 7 points is 4 times the probability of getting 5 points. So we need to convert that now into an algebra statement. So who's the bigger one here? So it's like we're trying to relate X to Y here, but one of them is bigger than the other, right? So this is the way to interpret this statement. 7 points is 4 times the probability of getting 5 points. Okay, so X is a bigger value, so it's Y that needs a 4 to be made equal. So let me study that and make sure it's correct. 7 points is 4 times the probability of getting 5 points. Yeah. So if you read that carefully, pause the video because this is a really important trick I'm showing you here. So when you read a statement like this, all you got to do is work out in your head who are they saying is bigger. They're saying getting the 7 points is 4 times the probability of getting 5 points. So x is the bigger number. So for you to set them equal, because x is the bigger number, you have to do something to y to make it bigger. And so you multiply it by 4. So hopefully that makes sense to people. Okay. Right, so then when you get information like that, always important to update your table. All right, update your table like that. Right, work out the value of z, the probability of getting, oh yeah, so then tells us the expected value. So we'll write out our expected value thing. E of x, we call it. Expected value is, so maybe not the best name in this question because x is already taken, but we'll roll with it anyways. So it's the amount you get by the probability of getting it, plus the amount you get here by the probability of getting it, and then the amount you get by the probability of getting it, which is z. And all that's equal to this number they say in the question, 1.155. Okay, so the great thing is this goes to 0 here. Because, 0 times z is 0. So we've really just got an equation here on y. I see 28y here, and I see 5y, so that's 33y equals this awkward number here. So then we have y. And when we have y, we have x. So that's happy days. Divided by 33. So this works out as a reasonable number. It's a nice fraction. You wouldn't want to write that as a decimal. So y is this. So then if x is 4 times that, x is 28 over 200. You could simplify it if you wanted. So what's z? Well, the idea is all of these should add up to what? All of them should add up to 1 because they're the 3 scenarios. All their probabilities should add up to 1. So you can very easily get z by just going 1 minus the 2 of these guys. Okay, so you could even do that in your head. These guys are 28 plus 7, 35 over 200. So in my head, this is working out as 165 over 200. And then I'll let the calculator tidy that up. So that's z is 33 over 40. Okay. All right, let me clear this away. Hopefully that made sense to people, particularly that cool trick with how to set x equal to 4y. Okay. Reading the question slowly to see who's bigger than who, and then pumping up the guy that's smaller. Okay. Okay, so now that's cleared away. So if we scroll on down here, there's another part of this question here. So it's still going on about the rugby thing, but they're changing up what they're asking. So they say the coach of the rugby team must pick 3 forwards from a total of 7 possible forwards on the panel. How many different combinations of the 3 forwards can they pick? Okay, so obviously pause the video, give both these parts a go. So this first one's pretty easy. This is just like, how many ways are there of picking 3 people from 7? It's 7, choose 3. It's a nice, easy question. But then the next part will probably take a little bit of thinking, as it usually goes. It's part 2 here. On Saturday, the coach picks 3 forwards at random from the 7. On Sunday, he picks, again, 3 forwards at random. Okay, so he just does the same thing on Sunday. And then you're asked to find the probability that no forward is picked on both days. Okay, so basically what you want to do is you want to make sure that on Sunday you don't pick any of the forwards that you picked on Saturday. Okay, so if we think about this, right, so the coach has picked 3 forwards on Saturday. He cannot pick those 3 forwards again on Sunday. So how many people does he have to choose from on Sunday? He only has 4 people to choose from on Sunday if he's not to pick one of the forwards he picked yesterday. So he has only really 4 people to choose from, and then we choose 3 of them because we need to make a panel of 3 forwards, okay? Hopefully that makes sense to people. That's your options for Sunday. This is what he has to pick, okay? And then we divide that then, because we're asked for the probability, not just the number of ways he can pick this. The number of ways he can pick this by not picking the forwards from Saturday is 4, choose 3. But the probability of doing this is divided by the total number of ways of just picking the panel, which is 7, choose 3. Okay, so that's kind of a usual pattern sometimes for these type of questions. In the part I, they'll get you to work out like the general overall way of picking 3 people from 7, right? And that will sometimes be the thing you'll be dividing by down here when you're doing a probability scenario. Okay, and on top then will be the unique thing based on what they speak about. There's a bit of a pattern in past papers for that. Um, so hopefully that makes sense. I'm sure people get the 4 choose 3. You know, there's 3 people we cannot pick, so we've only really 4 to pick from. So 4 choose 3. But then the dividing it by 7 choose 3. If you sit with it for a second, it'll make sense. Um, it's the number of ways of doing specifically what you want to happen over the number of ways of doing it overall, which we worked out in part I. Okay, so let's type that into a calculator and then we'll move on. 4 choose 3 over 7 choose 3, and that is 4 over 35. Okay, great, and that's a probability because it's less than 1. Okay, right, I'll clear this away. Okay, so scrolling along here, we've gone to further in document 2023 mock paper 2. So we have an interesting one here with the playing cards. So pause video, give them a go. They're kind of interested in these combination type questions. They can come up. So 52 playing cards in a pack. 3 cards are drawn at random without replacement. Okay, so that's important, the without replacement. So basically, whatever card was drawn first changes the outcome, the probability of the next draw. You know, so there's dependence. They're dependent. Okay, so the 3 cards are very specifically the Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds, right? That's a very specific scenario. And this is a combination as well. This isn't a permutation. The order doesn't matter. They're not saying you have to draw the Jack first, then the Queen, then the King. You can draw them in any order, okay? Just as long as you get those 3 cards. So that's a combination. So what we've got to do here, the way these probability questions work out, the best way to do them is you divide by the number of way of drawing 3 cards from the full pack, which is 52, choose 3. That's the number of ways of doing it. And then on top you have the number of ways of doing specifically what you want to do. So if you want to think about it, there's kind of 2 ways of thinking about this. So there's 1 Jack of Diamonds, it's like 1 choose 1, and there's 1 Queen of Diamonds, like 1 choose 1, and then it's 1 King of Diamonds. So 1 choose 1. Or another way of doing it, it's like on top, and because all of that you should know, 1 choose 1 works out as 1. I had to just double check that. So you could also have put this in as 3 choose 3. Okay, because there's 3 cards you want. We choose all 3 of the ones you want, you know. So it's like the specific scenario you want to happen. Right, so that's hopefully makes sense to people. So it's basically 1 over 52 choose 3. So that's 1 over 22100. Fraction is neater than a decimal. Right, easy enough one here now again. So it says the 3 cards are aces. Right, how many aces are there in the deck? There's 4. So we just want to choose 3 of them. So it's 4, choose 3, or yeah, from the 4 aces, choose 3 of them, and divide that by the number of ways of choosing 3 cards from the full deck. So it's the specific event you want to happen on top, divided by the number of ways of just, you know, picking 3 from the pack. So let's type that into calculator. 4 choose 3 should be 1. So 52 to 3. So I'm getting 1 over 5525 there. Okay, so then part 2 here. 2 cards are black and 1 is a diamond. So this would be a much trickier question if there was an intersection that could happen here, as in 2 cards are red and 1 is a diamond. That would take a little bit more thinking, because you could also be a diamond and a red card. So you gotta like pause when something like that, like there's an intersection possible, but not here. You can't be a diamond and then also be one of these black cards. Okay. So the way to do this is we want to pick out, see this word and as well here. So that means we're going to be multiplying something. So we want to pick 2 cards from the black cards. So there's 26 black cards. Choose 2 of them, and so we're going to multiply this together with picking 1 diamond, which is 13 choose 1. And then we'll divide that with the total number of ways of picking out 3 cards from the pack. Okay, so yeah, these kind of questions, they take a bit of practice, you know. You'll find loads of them in your textbooks, and also if you go through the past papers. So that there is working out as 13 over 68. Okay, so it's pretty big compared to the other probabilities. The 3 cards are the same color. Right. So the way I like to think about this is it's like pick one of the colors, okay? So the three cards are the same color, so pick one of the colors. So it's like two choose one of the colors. So, and then once you've chosen that color, pick three cards from that color. So there's 26 in each color. Pick the three cards from it, okay? So that's one way of looking at this problem. 52, choose three then on the bottom for the number of ways of doing it. So two choose one is like pick one of the colors, and now that you've picked a color, then pick three cards from the number of cards in that color. There's 26 in each, um, so that will give the same answer as this. There's another way of thinking about this. There's two ways of doing this. You can do it where you pick three red cards, or, see I used the word or three black cards. Okay, so or would mean add. So we can do 26, choose three if we want to pick three red cards, or 26, choose three if we want to pick three black cards. And then we divide that by 52, choose three. Okay, so and again, two, you should know two choose one is two, so you can see why they work out to be the exact same thing. Two times this is the same as adding it to itself twice. So let's type that into calculator. 26 C3 over 52 C3. So that works out as 4 over 17 as an answer. Okay, so hopefully people are okay with that. There might be a few more questions like that in the document, but we'll crack on here and we'll find a few more questions to do. Okay, I'll clear this away. Okay, so scrolling along then just a little bit after this, there's this deferred paper. So I highlighted this. This is interesting because it's given probability and it's got a not statement in it. You can call that a complement, but it's just better kind of call it maybe a not. It's easier to understand what it's not a, that kind of thing, you know. Anyways, let's have a look at what's going on here. So we got two events, A and B, Venn diagram. The probability of each is written in the region, so we don't have to fill that in. And then it gives, for example, from the diagram, the probability that neither of these happens is this. Okay, so they told us this, but they didn't have to tell us that. Um, we could have seen that ourselves. So basically, the way to understand this, when we say A union B not, it sort of means visually shade in everywhere A union B is. And then when you put the not there, it means everything I haven't shaded in blue. So A union B not is everything not shaded in. So it will be this region out here. So that's why it's 0.27. So the shading is a very important thing when you're doing these Venn diagram questions. Right, so what do we got down here? Find the value of the probability of A naught given B. That's given when it's a straight line, where a complement is, A naught. So we have a formula. I've introduced it in the part one anyways of the video. So it's the given probability formula. It's a very easy formula to remember. On top, it's always the intersection of these two guys. So there's two things mentioned here. It's always their intersection written on top, and it's always divided by the last guy mentioned. The last guy mentioned here is the B, so we divide it by the probability of B. So if you want to get, say, probability of X given Y, it's just X intersect Y on top, and then it's divided by probability of Y, So pretty easy formula to remember. Okay. So we need to get these two things, and then we have our answer. So what we're asking for here is where does A naught, what's not in A, intersect what's in B? Now the way you get something like this is you use the shading again. So I'm going to shade in everything that's A naught, right? Everything that's not in A. So it's all this region here. All right. Basically, I am putting yellow marks everywhere that doesn't go into that A circle there, right? Now I'm going to shade in B, right? All of this here in green is B. Now we're asking where does A naught intersect B? And you just look at your diagram and see where did the green dashes intersect the pink dashes. And if you study that carefully, there's only one place, it's there. Okay, that's where B and A naught intersect. So that top thing there, I've kind of ran out of a bit of room here, I'll come over here. A naught given B is equal to what we've seen there, 0.33 from the shading. And then we just divide that then by the probability of B. Probability of B is pretty straightforward. It's just all of B's circle. So that's just 22 plus 33, which is 0.55. Okie doke. and that works out, it's probably a straightforward number, is it? 0.55. Yeah, it's 3/5. Now I'll write it as 3/5, but it's maybe no harm writing it as 0.6 because the question itself is in decimals, you know. But you get the best of both worlds if you write it as 3/5 and 0.6, you know. So that shading thing is a very important thing for people there, you know, when you're finding intersections of things to be shading stuff in. Um, really, really important technique. Okay, so we have a part C here. Pause the video, give it a go, of course. C and D are independent, right? And that's not talking about what's up here. So this seems to be another question altogether. C and D are independent events such that C is this and the union is this. Find probability of D. Right. When you know they're independent, a specific formula works. This formula works. Probability of C intersection is equal to the two guys' probability multiplied together. That formula will only work when they're independent, right? So what do we have then? And then we also have a formula that always works for their union. So we know that probability of C union D is always equal to probability of C plus the probability of D, take away their intersection. C intersect D. Right. So we have certain things we can kind of sub in here, and you'll see how this works. So in for, let me get a good color for this. In for C union D, I'm going to put the 0.85. In for probability of C, I'm going to put 0.5. And then we're looking for probability D, so you could actually call that X. You do this a bit neater for the examiner. I don't have the space you have down here with the way the camera's set up. So probability of D equals X, so then you go plus X here, and then minus the intersection. So we know the intersection is this formula here. So then it's really, if you're happy with this, it's 0.5 times X, so it's minus 0.5 X. And now look at the blue thing, it's one equation, one unknown X, and you can find X from this. So what could you do here? You have a full X, take away half of X, and you bring this over, so you get something like 0.35 equals 0.5x, and then you just divide this by 0.5. It should work out as 0.7 in my head. Okay, and remember, what is x? X is this here, so the probability of D is 0.7. Okay, really important type of question that. So good that you've seen that there. Okay, that was a pretty good one from that year. Okay, so, and there's no other parts, so I'm gonna pause the video now and scroll along. Okay, so scrolling along, this is our next question here from this 2023 deferred paper. So it's a multiple choice test of 15 questions. Each question then has 5 possible answers and only one's correct. Typical stuff. So if the candidate picks the correct answer, they get 10 points. If they pick an incorrect answer, they lose points. So this is an interesting one here. This is what we call negative marking, where if you don't know the answer, you're actually sometimes better not answer it at all. Don't be guessing, because if you guess and get it wrong, you lose points. So that's called negative marking. And that's very useful for these multiple choice tests to stop people guessing answers and getting marks they shouldn't be getting from guesses. Anyways, candidates must answer all questions, okay? They must answer all questions. So that's interesting there. So they're kind of being forced to give an answer. They're being forced to guess. So it's hard to know. That's just helping us solve the probability question, but whether or not that's a real life thing, where they're forcing someone to guess if they don't know the answer, that wouldn't be appropriate. Candidates get a positive or negative score. Can get, yeah, so you can. Basically, you can get lower than 0 is what they're saying there. Okay, so find the expected value, expected score of a test candidate who randomly selects an answer for every single question, right? Okay, so what you got to realize here, if there's only one correct answer out of 5, so you have a 1 in 5 chance of getting it correct, and you have a 4 in 5 chance of getting it wrong. Okay, so that's incorrect. Right, so you just basically do a kind of an E of X on this, right? So your expected value for this. So you could look at, say, question 1, for example. Yeah, it's like, you know, every time you, so there's a quick way I can just kind of write this down and explain it after. So you get, what's the easiest way to write this down? So it's a bit like, if we just do question 1, for example, here. So you have a 1/5 of a chance of getting 10 points, and then you have 4/5 of a chance plus, and in the expected value formula we always sum things, so I'll write the expected value formula for people that don't know it. E of x equals the sum, this is why there's always pluses in between, the sum of x multiplied by the probability of x. So it's the value you get multiplied by the probability of getting it. So we here have this is the other way around here, but you get a value of plus 10 points, but you only get that 1/5 of the time. And then over here, plus 4/5 of the time, you'll get a score of -2. So that's just your question 1. And then you kind of move that on here. So the question 2 will look the exact same. It's like you have 1/5 of a chance of getting a 10, and then it's plus 4/5 of getting a -2. So rather than, writing that out for all 15 questions, because it's just going to be the same thing I write out every time, you could just stop there and then take this entire thing and multiply it by that through the 15 questions, okay? So let's do that. So you can even see a little bit of what that works out to be. So it's 10 over 5 minus 8 over 5 times 15. So 6 marks. So the expected value, if you guess everything on, you'll get 6 points. 6 points. Okay. Hopefully that makes sense to people. Very interesting question, that. So yeah. So basically, what I wrote that it's x times the probability of x, but in the formula here I've written the probability first and then the times the value you get the x. So again, if expected value questions, they're pretty straightforward. So if they're a bit confusing for you there, have a look at a few of them in the textbook and get polished up on them. Great, we'll move along. So is there a part 2 to this? There's not. So let me pause and move along. Okay, so I've moved along here. This is still part of this 2023, which is a little bit further down. Now I have a note up here to remind you of the Bernoulli trials rules, and I'm not actually going to do that in this question here. There's a question later on in the document where we'll be talking about the rules. You're meant to know kind of the 4 conditions for when something's a Bernoulli trial off by heart, and I'll show you that later. Maybe not in this video, but it'll be like in a future part overall of going through this. So it might be in this part or it'll be in the next part, because this is part 2 of the video, so it might be in part 3, that kind of thing. Okay, so this is clearly a Bernoulli trial. You can read them, they're very repetitive. People are chosen at random from Ireland, probability to wear contact lenses. So there's your probability of success there, 2/5, 2 over 25, okay? If 10 people, there's your N, if 10 people are chosen at random, find the probability that, see this buzzword, exactly, 2 of them wear contact lenses. So this is 2 successes out of 10 attempts. They're so straightforward. So you go probability of exactly 2 equals 10 events, choose 2 successes, probability of success to the power of 2, probability of failure, power of 8. It's so repetitive, these type of questions, and they come up so much, so you want to be really on top of these and have practiced a load of them and got them right, and be feeling confident and happy when you see these come up. 23 over 25 power of 8. So that's coming out as a decimal, and that's good because they want us to give it to 4 decimal places. 1478. Okay. Now this is a great question down here. This is what we want. I remember at the very beginning of this video here, we had the rugby match, but it wasn't a good question because it was like the very first miss occurred on like whatever the 4th attempt, where this is what we want. Find the probability that the 7th person chosen is the 2nd person who wears contact lenses, okay? So this is like the example with an archer, that he gets his 2nd score on his 7th attempt. So what this really means, people, is that in 6 people, we've only had 1 of them who's got a contact lens. And then comes the 7th person, they will have a contact lens. So that's what you've got to understand. To do a question like this, you've got to work out what's happened before the 7th person. So if the 7th person is to be the 2nd one who wears contact lenses, that means in 6 people, you've only had 1 person who wears contact lenses. So that's kind of 6 successes. That's only 1 success in 6 attempts. So that would look like this. 2 over 25 to the 1. 23 over 25 to the 5. So what is that I've written there? That is the probability that in 6 people picked, there's only one contact lens among them, one contact lens person. So then comes our 7th person, and the way we account for a 7th person is we take this big unit and we multiply it by what happened with the 7th person. Here comes the 7th person, and that's why I'm multiplying, and they wore contact lenses. And that's it. That's all it is. So let's type that into my calculator now. 6 choose 1 is 6. So some of this is easy type in, you know. Times 23 over 25 power 5. And then multiply that by 2 over 25. So if I've typed that in correctly, I get this number of 0.0253. Okay, great. Let's clear that away. So there's another very good question here down the bottom. And definitely give this a go. Pause the video, give this a go, okay? Find the minimum number of people. Okay, we're looking for n there, hopefully you realize. The minimum number of people who would need to be chosen in order to be at least 90% certain of including at least one person who wears contact lenses, right? Right, so we need to, pretty tough question, right? So we're seeing this at least here. It's a big buzzword in probability. At least one. Anytime we see at least one, you can be pretty sure there's this one minus the probability of none coming into it, okay? That's your at least once language. And then in this type of a question, it's probability of exactly 0. None wearing contact lenses is exactly 0. So what we've got to do is this, and exactly 0 people wearing contact lenses. Say if you had 5 people that don't wear contact lenses, right? That's 23 to the 25 to the power 5. That's just 5. You picked 5 people at random, and all 5 of them didn't wear contact lenses. It's as simple as that. He didn't wear them, and he didn't wear them. You're just multiplying 23 over 25 by itself 5 times, right? If we're doing this for n people, it's the power of n, okay? So that's what we've got down here. Hopefully people can realize. What we're dealing with down here, when we're looking for the probability of at least 1, we're going 1 minus none in n people. Okay, so it's 1 minus this, right? And we're told that this has to be at least, we're looking for n is the question mark here. This number has to be at least 70%. So we want to set this equal to 0.9, and we'll work out the at least thing here. We won't use an inequality symbol for the minute. So where is n? N is in the power, so we need to use our logs. So let's tidy this up. I'm going to bring this over here, so then I get 0.1 equals 23 over 25 to the n. So using logs here, the power goes on its own when you use logs. That's the whole point of logs. Who's the base here? The base of 23 over 25, that stays as the base here. And then that leaves room for the other guy, the 0.1. So we work this out here. So n is supposed to be 23 over 25. So 27.615. Now, this is the big thing you've got to understand here, okay? There are 2 possible answers to this type of question. So this type of question comes up, they like examining it, and they need the student to always check this. You don't just round up or down, you check. Is the answer 27 or is it 28? And you need to investigate this. So you need to put both of these back into the original expression up here. And you got to study which one actually does make it either fall above 0.9 or below it. And you got to read it here very carefully in order to be at least 90%. So what they're looking for is a value that makes it over 90%. Okay, so if I put 27 in there, if I go 1 minus 23 over 25 to the power of 27. So when you use 27, what this works out as up here is 0.8947. Now, what do we think there, people? Has that gone at least 90%? No, it hasn't. We need it to go over 90%. If we put 28 in here, though, for n, we get this number of 0.903. We'll round it up to 2 then. Now that's a tick, because that now, once we hit 28, we are in the at least 90%. So the answer to this question is 28. Okay, but the examiner needs to see you testing that out, okay, because sometimes the question could be worded in a funny way where it was actually the 27 that we wanted to be our answer. Okay, so it's never really a matter of just round up or down. You have to think about it. Um, Hopefully that makes sense to people. Um, okay, so really important questions examined there in 2023's deferred paper. Okay, so I think that's all that there. Question continues the next page. Okay, so it doesn't because of the way the study clicks thing works. So I'm gonna pause the video, scroll on to our next one. Okay, so we scrolled along here, we found the next question here with the red star beside it. Just for people who are interested, this is from 2022's paper. So these are good. These come up. These type of questions where they're giving you instructions in words and you have to convert them into kind of an algebra statement for your probability. It says B and G are unknowns. They're nice here. Sometimes you have to kind of make it up that it's B and G, but they're sometimes quite nice and they give you the variable names. Okay. Find the value of B and G. Right. So pause the video. Give this a go. Right, so we need to convert these statements into algebra we can work with. So 3/5 of the students in the class are girls, right? So how can we interpret that? So the number of people in the class are B plus G, right? So then if 3/5 of all the students are girls, we could kind of see, um, what's a good way of writing that? The number of girls over the total people in the class is equal to 3/5. So these questions take practice to be able to come up with statements like I did there, just kind of relatively quickly. So knowing B plus G was the total number of students in the class. So if you go the girls divided by the number of people in the class, you get the ratio of girls in the total class. So that was 3/5 there. Okay, what's next? 4 boys and 4 girls join the class, right? One student is then picked at random from the class. The probability that the student is a girl is now 4/5, right? So how do we interpret that statement? So what we've got now in the class is uh, there's really B plus G plus 4 plus 4. That's the total number of students in the class. The number of boys in the class is B plus 4. And the number of girls in the class is G plus 4. So if you're asked here the chance of picking a girl out of this new classroom, it's really G plus 4 divided by the total number of students in the class, which is B plus G plus 8. And that's equal to this probability here, 4/7. And this is great now because you'd be kind of happy in an exam situation here because now you've got how many equations? 2. And how many unknowns? 2. So you can actually find B and G from this information. So just a bit of algebra now. So let's cross multiply here. So we get 5G equals 3B plus 3G. Bring this over. You get 2G equals 3B. Okay, we'll come back to this in a second. We'll cross multiply here. We'll get 4B plus 4G plus 32 equals 7G plus 28. Plus 28. Hopefully these are all calculated correctly. I might bring what's the best way to do this? I'll bring the G's maybe over here. And I'll keep the numbers this side. 4B plus 4, then when you bring the 28 over, 4B, and then you get equals 3G. So then kind of circle up your tidied up equations for you and the examiner. Okay, so it's really just a junior cert problem from here now. What's the quickest way to get this solved? Probably I'll just do it rather than kind of multiplying one and then multiplying the other. I'm just going to get maybe G on its own here. So G is equal to 3B over 2. I'm just going to put that in for G here, okay? So then I get 4B plus 4 equals 3 times this here. So that's, you'd want to show it for the examiner as well, so everyone knows what you've done, okay? So you put this in for G here. So then your next line here, of course I don't have the space, so I'm going to just write it as I'm writing it. And then that equals 9B over 2. You'd multiply both sides by 2, and you get something like 8B plus 8 equals 9B. And then you just bring this over and you see that B is 8. Great. And where's the best place to put this information? Down here when you've got your G on its own. So you can do this in your head. What's 3 times 8? 24 divided by 2, so G is 12. So there's originally 8 boys in the class and then 12 girls. Great. Yeah, the hardest part of that question is writing the pink thing here and the green thing. After that, it's a junior cert problem, you know. Okay, hopefully people enjoy that. Let me clear it away. There's a lot of stuff on the screen. Okay, so I scrolled on down here to this question. Now, I'm not going to, as you can see, this is a mock paper, but there's a lot of stuff to kind of fill in here, and then we fill in all the stuff on the Venn diagram. I'm not going to do that. I'm just going to show you the shading stuff, which is the more important thing you got to know. Now, I've marked this one down here for just a bit of shading, but I've seen this up here that's very interesting. So I want people to read part 2 and think about, and pause the video and think about what it does to the Venn diagram down here if A and C are mutually exclusive. Okay, so hopefully you remember this diagram here. If they're mutually exclusive, it means they have no intersection, right? If this is A and this is C, this is what mutually exclusive. It means they agree to not include one another. So when you're mutually exclusive, it means your intersection is 0. A intersect C is equal to 0. There's no intersection. So if we're told here A and C are mutually exclusive, that means this entire region here that I'm shading, all of that is a big 0. There's nothing in there. There can't be any number placed in there because A and C have no intersection. Okay, so that's just an interesting thing there. Hopefully you realize that. Right, we're talking about B union C not here, and I want to walk you through how to identify this region with shading. So let me highlight B union C first here with pink before I shade it. So it's nice to go around it. All of this here is B union C. So we're going to shade that in there. And so when you're asked B union C not, it's basically every region that's not in there. So it'll be this little bit of A, and it'll be everything outside here. So that's the shading for you there. So basically you would just add up whatever number was here and whatever number was out here, and you get your answer there. So the shading's a big thing, particularly with these complements, the not. Okay, easy stuff. So I'm going to scroll along here, find our next one. Okay, so scroll along through the document. I found this, our next question here. It comes from a mock paper in 2021. So this is a very kind of interesting question, and it's going to be nice to see how particularly the part 2 works out. Part 1 as well takes a bit of thinking to draw it out properly. So definitely be pausing the video, giving both of these a go. So I'm going to go through the part 1 here. So some very interesting stuff you'll see here. So the attendance at a local rugby match is dependent on the weather, as you'd imagine, yeah, real life scenario. The probability of a large crowd attending if it is raining is this. Now that's a conditional probability. So what you got to do here is you kind of divine two events and tell the examiner them. So let L be a large crowd attending, okay? Large crowd, okay? And let R be that it's raining, okay? That's what them symbols stand for. So what we've just been told here is the probability of a large crowd attending if it is raining, that means given it's raining. So that would be written like this. That's the proper way to record this statement into a probability thing. So it's the probability that a large crowd attended, given, straight line, it was raining, was 0.35, right? I'll tidy up that 5. Okay, we continue reading. The probability of rain on a match day is 0.3. So what that probably means there is just the probability of raining. Because it's kind of given, you know, this is a match day scenario kind of thing. So they basically just told us the probability of it raining is a 30% chance of rain. Okay. Okay. Right. And then what are they asking for? Find the probability of rain and a large crowd. And see the and. So and in probability means intersection as well when we're writing these statements. So we want rain and a large crowd. So what we're really looking for here, and you pick up a ton of marks from the examiner just identifying this stuff. We're looking for probability of it raining and intersect a large crowd, and you put a question mark beside that. Okay, so we have extracted all the info from the question. So what can we do? Well, we know a formula that works for this here, the given probability. We can say L given R is always equal to the intersection of the two things Divide it by the last thing mentioned, which is or. Now, one thing we've got to know as well is, if you didn't know this, L intersect or is the exact same thing as or intersect L. There's no difference. So you can make a flashcard on that if you didn't know it. That L intersect or means the same thing as or intersect L. You know, it's the same thing. So we could probably sub into this if we want it and then move it around if that helps people. So we know this thing here is 0.35. We know this is L intersect or. And then on the bottom here is probability of raining, which is 0.3. So then we can get our L intersect or, which is what we really want up here, or intersect L, the same thing. So then probability of L intersect or, when you move this around, is just the two things multiplied by one another. 35 times 0.3. Okay, and then that is, you can just write it here, it's the same thing, or NL is 0.35 times 0.3. So I'd write that as a fraction, but given things are in decimals here in this question, we'll stay in decimals. And this isn't a messy decimal, so I'll leave it like that. Right. Absolutely. I'm sure some people would have just looked at this question and realized all you got to do is just multiply the two things together. And that, yeah, that's completely fine. Okay, if you've seen that. But it's also very worth your while having seen me write out the statements like this here and see why it is as simple as just multiply the two probabilities in the question that they gave you together and you get your answer. Okay, so yeah, hopefully that helped people there. Now it's a nice interesting example. So what do we got down here now? Let me try and do another snip of that where I can kind of bring in a little bit of our bottom question here now. So yeah, let me get that set up there at a good height. Okay, so yeah, so that looks good. I've made some good space there. So it says here, the probability of a large crowd attending is 0.8. Okay, so that seems like we still see this is part 2 as well. So we probably need our answers from the previous question. Let me see, can I get them back here? I don't seem to be. So I kind of remember most of them anyway. So probability of it raining was 0.3, wasn't it? Probability of L given or was the 0.35, if I remember. And then the thing we worked out was rain and a large crowd, or NL, intersect, was equal to the 0.105, if I remember correctly. Now we've been given another thing now. We've been given probability of the large crowd attending on any match day is 0.8. So now we're asked to verify that the large crowd attending and it raining occurring are not independent. So how would you do this? So hopefully you've given this a go. There is a formula that should work if they were independent. And the formula that should always work if you're independent is your intersections. So we have or intersect L should always be equal to just the two probabilities multiplied by one another. Now this formula doesn't always work. This formula will only work if they're independent. Okay? If they're independent, that formula will work. So the way you do this is you actually use the formula to see what happens. So you work it out using assuming they're independent, or NL equals it raining, which is 0.3, and you multiply it by the probability of the large crowd. You can do that in your head. 3 by 8 is 24, so it's 0.24, I believe. And this is it here. This, if you had another line here, this does not equal 0.105, which we worked out earlier on as probability of or NL. So the fact is, using this formula, we got a different answer to what we already know or NL to be. So this would actually be pretty much full marks. The examiner would understand what you've done here. This line is very important, where you worked out this new value is 0.24 using a formula you shouldn't have used because they weren't in. Well, you used a formula if they were independent should have worked. Because it did not work, it means they're not independent. Okay, so you can spell out the word independent there, or you could just write dependent. Okay, great. Yeah, very good question there. That was smart there. So hopefully people learned a lot from that one. So what's the video on there? 52 minutes. So what I'll do, I'll scroll down to our next question, and then we'll pick up part 3 of the video from that there. So let me find our next question. Yeah, so I scrolled down a bit further here, so not didn't have to go too far. So this 2021 mock paper two, and there's a looks like an expected value question here. Would you play the game? Like, is it a fair game kind of thing, you know? So we'll be working out expected value here. So I'm going to pick this up in part three of the video. So thanks for watching. Hope you made some good flashcards and some good learning from this one, and we'll see you in the next part. Bye now. Okay, so we're back for part three of important past paper questions you should know on the topic of probability that come up. So as you said, we pick up from this question here, which is on an expected value type problem. So as always, be pausing the videos and giving them a go yourself. Giving the problems a go yourself ahead of me doing them. So we're told the game consists of a colored die being rolled. 3 of the sides are red, 2 green, 1 blue. If you get red, you lose. If you get green, you get €2. And if you get blue, you get the fiver. Okay, the charge to play the game is 150. Would you play the game? Explain your answer. Right, so this is, we work out an expected value here. We call it E of X like this. And it's really just whatever X's value is multiplied by the probability of getting that value. Okay, and you sum it together. So there's going to be loads of things adding together. So that's the big E there means. So if we work this out, we get that you can win €0. So that's what the X is. And you win that half of the time. So 3/6, if that makes sense. Because there's, if you get a red, you get €0 and there's 3 reds. This is the plus here. That's this big E action. You get €2 and you get €2 2/6 of the time because there's 2 green faces. Yeah. And then add, there's another, this is the plus action. And then you get a €5, but only 1/6 of the time. So this is every time you play the game, on average, this is how much you expect to make from playing it. So let's multiply that together. What's that going to give? 4/6 plus 5/6. And that works out as, and that has units as well. It has units of euros. Okay. Because these numbers here, the 0, the 2, and the 5 had units of euros. The probabilities are unitless. So 150. And if it costs €1.50 to play the game, this is what you would call a fair game. Okay. If the cost to play the game is equal to the expected value of the game, we call that a fair game, okay? And so that's what the examiner is expecting you to explain here. You say, yes, I play the game, and you play it because the expected value is equal to the cost to play the game. Okay, the cost to play, so therefore it's fair, okay? You'd write that out in clear language, obviously, for your exam. Okay, so that was a good question. So I'm going to pause the video, scroll on to our next one. Okay, so I scrolled along and found our next question here. It comes from 2020 mock paper 2. So this is a very good question. So I took a second to read this before getting it set up here, and I tell you this is a very good question. So definitely have a go at trying this. This is definitely one you want to have a go at trying to do out. It's quite tough. But like it's the kind of question that even if you don't get it fully out, you can still pick up a ton of marks, you know. And this, if there's 25 marks for all question 1, there might be just 15 marks for this. So you could actually pick up 10 marks of this by just doing some pretty good attempt marks, if that makes sense. Okay. So let's get it set up here. But yeah, very very good, very well thought up question this. Okay. So we're given there's 4 things here that we're given, and we need to somehow get them on the page. So in a random sample, it was found that 55% of respondents were male and 45% were female. So we need to convert that to something. So we're going to define something as M being male, okay? And F being female, of course. So then you could say then the probability of being male is 0.55. And then the probability of being female is 0.45, right? Based in this world of where they took this sample. So that's important to kind of extract that from the question there, okay? That's what they gave you in that first sentence. So now what they give you in the next thing is a little complicated here. They say 75% of the males who were surveyed, and we'll just read one part of it here. 75% of the males who were surveyed read the local paper. Okay, so what does that mean? How do we convert that? That's a given statement, but we need to work out how to make sense of it. So what this is saying is given they were male, 75% of them read the paper. So it's one of those things where you got to kind of sit with it and think about it for a second. So what they're really telling you there is the probability that you read the paper given you're male is 75%. So hopefully that makes sense to people. And then, but this other thing is here, 62.5% of females surveyed read the newspaper. So again, the probability of you reading this given you're female is 0.625. So it's a little complicated to think about that, but that's what they're talking about. This is the probability of reading the newspaper, and then they're giving a breakdown of whether you're male or female. So this is the given, okay? Right, that's what was tricky about that one there for sure. So then there's going to be our question mark here, what we're actually looking for in the question. If a person is chosen at random, what is the probability the person is female given they read the newspaper? Okay, so we can do that we can write that into a statement. Person chosen random is female given they read the newspaper. So R stands for read, as you kind of picked up. And we put a question mark there. So you actually pick up a nice bit of marks from the examiner, just kind of getting the problem set up like this. You know, these were tough here to kind of make sense of them. Okay. Right. So let's pull our question mark apart. What's the thing we're actually looking for here? So we should know that the given formula is always the intersection of the two things mentioned. So F intersect R divided by the last thing mentioned, which is R. So that R should look a little bit better. So divided by the last thing mentioned here, which is R. So this is the probability of R. So do we have any of these? No, we don't have any of these. So if we need to get these two things to get our answer, right? So we could probably use this statement here to help us. Okay, so we've somehow used this information here that we're given here on the left to get the thing we're looking for here. Okay, so if we get F intersect R's probability and probability of R, we solve the question. We've got our question mark. Right, so let's pull this thing apart. So what do we got? We know that probability of R given F is equal to probability of their intersection over the last thing mentioned, which is probability of F. Now this is great because R intersect F is the same as F intersect R, right? So this, if we can get this, this is one of the things we're looking for. Now, the good thing about this is we already have this and this, as you can see here from our list of things we have. So I can just move this around and I can write that the probability, and I'll write it like this for a second, R intersect F is really just equal to the probability of R given F, when you move it around here, multiplied by the probability of F. Okay? And we know those values there. This is 0.625 multiplied by probability being female, which is 4.5. So again, you're just kind of solving through the algebra here, following the instructions of what your algebra is telling you to do. 625 multiplied by 0.45. So because the question is kind of in decimals, instead of writing this as a fraction, I'll write it as this awkward looking decimal, but there's no need to round that because that's actually all the decimals it has. So you'd write it down fully like that. Right, so that's great because that is this thing here. That is this thing here. So we found one of the pieces. And then you can just tell it for yourself and for the examiner that this thing here equals probability of F intersect R, right? So what's missing now? What do we need? Well, we need probability of R. So you kind of tell yourself now, okay, what's the goal? If I get this thing, I win. If you get the bottom thing here, you already have the top thing and you're after this thing. So this is the only missing piece of the puzzle. And again, you're picking up a lot of marks off the examiner, getting closer to what you need, okay? So because we used this statement, it might make sense now in our next piece of work to see can we get anything going out of this statement here. So we'll do the same job on that one. We'll go probability of R given M will be equal to their intersection or intersect M over probability of M. And yeah, we can work something out from this. We don't know yet how we're going to use it, but we do have probability of M and we do have the probability of R given M. So we can work out their R intersect M even though we don't know why we need it, but we'll work it out here. and then we'll see is it useful in a second. So if we can work something like this out, why not get it, you know? So that will be basically just these two things when I multiply up by the PM. So I'll just do that quickly here. So that will be this guy, 0.75, multiplied by this guy's bottom when you bring it up, which is the male, so that's 0.55. So then that equals, so it's getting a bit messy on the screen. As I said, this is a tough problem. There's a lot going on here. So in decimal, keeping in decimals, this is 4125. Right, that's the probability of or intersect M. So now what you might do here is, you know, you might hit a bit of a wall, right? You're like, right, I need probability of or, but I'm kind of just after getting these two things that I don't really know. Like I'm getting this thing, I don't know how to use it, or intersect M. I knew I needed this F intersect or, but I don't know how to get probability of or. So pause the video, see can you come up with the smart. This is the really tough part of this question to realize. So have a go, see can you work out how you get or, probability of or from what's already on the screen. So this is pretty tough. So probability of or here in this question, that you've read the paper, is realistically just add up the people that read the paper that are male and the people that read the paper that are female. So it's these two things added together. So it's you've read the paper and you're a male, and add that or, so it's an or situation, or it's the probability that you've read the paper and you're a female. Okay, so you can be this group or this group, and they're the people who've read the paper. So a little bit tough. That is pretty tough to kind of think through that. So we actually have these two things here. So we have that you've read the paper and you're male. We just worked that out there. We were wondering how do we use it. So it's there. Read the paper intersect female. We worked that out earlier here. It was this number. So as I said, this is a tough question. 1, 2, 5. So now we have the probability that you read the paper. It's that number there. What's it? Probably like 6 something, 0.4125 plus 0.28125. So that works out as 0.69375. So now we have the two things. We went off and very difficult finding probability of or, and we've got the probability of F intersect or. It's this number down here. So we can sub those in there. Let me get a good color for that. I can use red here. So the intersect was this thing here, 0.28125 all over this new number we got here, which is 0.69375, and that is the answer to the question. So I'll just tidy it up. But yeah, very tough, very tough. But again, if you can't get that out fully, there was still loads of room to pick up a ton of marks in this question, you know. So that works out as 15 over 37, and then I'd also write it as the write it out fully here. So it's F given or, which we were after, and then I'd write it in the decimal format to kind of match the question. 0.4054. The reason the decimal isn't a good way to write this is because this isn't an exact decimal. If you type that in, you'll see there's loads of decimals, so I'm having to round there. So I would be putting 15 over 37 as my last answer. Okay, as I said, very tough question, but there was definitely lots you could get there to pick up some marks. But I have to say, this here was really tough to realize that that's how you got probability of or, you know. But there was a little bit of a hint because you got this thing and you're like, how do I use this, you know? So yeah. Anyways, make some notes on that question, and then if it comes up again, you're kind of prepared for it. You're prepared for this kind of a scenario here where you're looking for this, and this is actually the intersections added together. Okay, right. I'll clear that away and get us set up for the next question. Yeah, I was actually scrolling down here, and like this isn't one of my marks that I've put here, like with a red star, but just because I've seen it, and I've a few times, if you've been watching the previous parts I've been on about like the Archer question, it's such a good one for these Bernoulli trials, and so this is, you know, I kind of verbally discussed this question, so I said why not do it, even though we've already done one like this. That's why there's not an X here, because it's not a unique thing you haven't already seen me solve. So let's just put a mark here. And pause the video, everyone, and make sure you're able to do this, because this is bread and butter probability Bernoulli trial stuff you're meant to be able to do. Okay, it says calculate the probability that the archer, that his 5th hit will occur on his 9th shot. Okay, calculate to 2 decimal places. So what we got to do here is he's going to have, out of 8 attempts, right, he's going to have 4 hits, 4 successes, okay, 4 hits in 8 goes. right? 8 goals. In 8 attempts, you could say as well. And then on the ninth attempt, he'll get a hit again, okay? So the way we do this is in 8 attempts, we get 4 successes. A probability success is a hit, so that's 4/7. That's the power of 4. And then failure, we want 4 failures as well. Okay, so that there is literally what it says in the tin. This is the probability of getting 4 hits in 8 attempts. And now here he comes. We take this whole block. Here he comes for his 9th shot. He does this. He gets 8 attempts and 4 hits. And that's why I'm going to multiply here. And in his 9th shot, he just got a hit. So you just multiply by 4/7. Okay, so that is, I'm not going to type that into calculator, obviously. That's the answer, there's no need to, we've already done this type of question, but that there is really important, that you're able to make sense of that. If you want something to happen in the 9th throw, think about what happened in the previous 8 throws, that kind of thing. And then just multiply it by whatever happens in the 9th throw and what happened in the 9th throw. Okay, great. So I'm going to clear this away and get back to scrolling, finding our next question. Okay, great. I didn't have to scroll too far there. So this 2019 mock paper, I put 3 stars beside it because this is something you're meant to know. You're meant to know the properties of a Bernoulli trial, right? So there's usually 4 properties the way we define it. Now I'm going to get, you have to make a kind of flashcard on this and be pretty comfortable with this. So I'm going to actually pop to the book and get us our yellow thing to make a flashcard on if you don't know the answers to this. Okay, so 1 second. Okay, so this is from the book. When they talk about Bernoulli trials. So we're going to snip the important bit here so you can make your flashcard and note on this and then learn it off by heart. So Bernoulli trials usually have these 4 characteristics, right? There's only 2 outcomes. So obviously they've written it in a bit longer language here, but you can just write it in short language for your notes. There's only ever 2 outcomes, and we call the 2 outcomes success and failure, all right? And you can write that the probability of success we call P, and then this is Q, okay? But we'll mention that later. This is a really, really, really important thing. The trials are independent. That is a massive property of Bernoulli trials. So basically, let's say our archer we had there, right? If the archer scores, he is not more likely to score on his next attempt. He's not like he's gotten this boost of confidence now and he's more likely to hit the target. That's not Bernoulli trial stuff. Basically, he's so professional that if he misses or if he scores, he's just going to still have the same miss chance, score chance in his next shot, okay? So that's the independent thing. What happens before doesn't affect the next shot, the next trial, the next penalty, okay? So that's what this is about here. This ties in with this independent thing. Success and failure is constant, okay? Trial to trial. In other words, P's value, the success chance, doesn't change. And as well too, this is the last kind of thing people kind of forget this. There's meant to be a fixed number of trials, okay? You'll always be running these for n trials. So for example, in a scenario where there's not a fixed number of trials, say the person has to keep taking shots until he scores 7. That's not really a Bernoulli trial because we don't know how many shots he's going to have to take until he scores 7, So it's not a fixed number of trials. Whereas if we were asking a question, okay, he has 10 shots, 10 trials. Work out the probability of him scoring 7 times, that kind of thing. So hopefully that makes sense. So make a note then on all that. And then obviously from this here, it should make sense that P plus Q is 1. And the reason P plus Q is 1 is basically part 1 here, because there's only 2 outcomes, success and failure. Great. So back to our question in the book. Let me pause, or in the exam paper. Okay, so yeah, so obviously hammer out the 4 things. The list says list 2 properties, but you'd be mad to only list 2. You'd be right to list all 4, So 1, 2, 3, and 4, and literally write them out as I showed you there in the textbook, okay? And let the examiner look at 2 of them, give you 2 ticks, and then you're happy. Okay. And yeah, I think this next thing here, we've already done ones like this. This is very similar to the Archer question, Oh, it's actually that I made this up there is like 10 and 7, the chances of me making up an example, and it's the exact one here. That's a bit crazy. Okay, so yeah, so then that was tied to the Bernoulli thing. You can see that's very similar to the Archer one. Scores his 7th penalty on his 10th attempt. So that would be in 9 goals, he scores 6 penalties. We've already done that a second ago with the Archer. Now this is a bit different. This is a unique question. It's a kind of a standalone question. So this This is what we do, and there's only one part to it. So obviously, pause the video, give this one a go. I think this is a good question. Okay, so hopefully you gave that a go. So we're given a few things here. We're told there's two events, and we're given A given B and B given A, and we're given an intersection, and we're asked for this. Right. So first thing you might want to do here is write out what this thing is equal to. So this is your question mark, you know. So you always want to maybe expand on the question mark thing. So I'd write that that's a question mark in a line. So we should know this formula always works for this guy. It's the probability of A plus the probability of B, subtract the intersection. Probability of A intersect B. So to get we already have the intersection from the question they give us there, it's a 7. So we need to go and find these two things somehow. So let's somehow try and use these here. Right, we should know that the A given B can be written as the intersection of the two things divided by the last thing mentioned. So divided by the probability of B, because B is the last thing mentioned there. Okay, so then what can we get from this? Well, we know this guy's value. We know the intersection is a 7, so we can actually work out the probability of B from that. Probability of B, when we bring it up here, would be probability of A intersect B, and then bring this fella down underneath here. So hopefully you're okay with just how I moved that around there. And sure, we have these values. This thing's a 7th. This thing here, A given B, is a half. You should be able to do that in your head. You should know that's 2 7ths, okay? You should know that when there's a number down the bottom here, that really belongs up top. And when you have a fraction on top and has a number on the bottom, that's really on the bottom. But sure, if you didn't know that, you could just fire it into a calculator, you know? Great. So we can probably just do the same process then with the other guy. Let me switch up the colors. So we are dealing with B given A here. So intersection of the two things divided by the last thing mentioned. And then we'll do the same thing here because we have this guy from the question, and B intersect A, as I've already said to you, is the same as A intersect A. It's the same thing. So probability of A when you move it around would be the intersection of the two guys over B given A. And we sub them in from the question. This here is again a 7th, and then this thing here is a 3rd. And so again, that goes down there, the 3 comes up, and then that's 3 7ths. Great, so now we have probability of A. So then we just sub back into our original thing up here. So let me get a good color for this. Maybe I'll use black. So this is 3 7ths plus probability B, which we worked out as 2 7ths. And then take away the intersection, which was a 7th. Great, you can do that in your head. You don't need a calculator. 4 7ths is what that's going to give. Okay, 4 7ths. That's the answer. So that was quite cool there. So that's kind of bread and butter probability. So hopefully you were able to get that out. I'm sure if you watched the previous parts, you'd be pretty well trained up to have gotten that out. Okay, right, clear that away. Find our next question. Okay, so we're back. So I scrolled along there. We're at the 2019 mock paper 2 now. So this is another one of these letter things. So we already done one of these, and I think in part 1 of the video, we done the vowels must be together. Now I'll hammer it out again. It's a little bit annoying because this is 7 letters again, so it'll look very similar, that solution. But sure, we'll hammer this out because this is a pretty important question where you're like moving the letters around, you know. Right, and how many ways can the letters of this word be arranged? So there are, each letter is used once. So basically, I won't use black, I'll use red. 7 boxes because there's a 7-letter word here to be made. So this is when you have a permutation. Basically, the order of the letters matter, you know. And so we use these boxes and we multiply them together. So it's called the box method. Right, how many letters do we have that can go in the first slot? There's 7. We've used up one of our letters. Now there's just 6. 5, 4, 3, 2, and 1. So you should know that's 7 factorial. And 7 factorial in your calculator. 5040. Now this is a good one here. The letter H must be first. No problem. We'll whip out our boxes here. That has to be a 1. That has to be the letter H. H has to go there, okay? So that means then how many letters do we have to put here? We have 6. We have 5 options, 3 options, 3 options, 2 options, 1 option, okay? So when you look at that, that's really 1 times 6 factorial. So I'll type in 6 factorial into my calculator to get a quick answer here. 6 factorial. So that's coming in at 720. Great. So then the next one here is the vowels must be together. Now we've already done this kind of question here. And again, too, it's annoying because again, there's only, you know, there's still 2 vowels, so it's nearly identical to the question I done before. It'd be more interesting if there was 3 vowels here, you know. But yeah, I might mix this question up here. So I'll solve this first just in case anyone's doing it. So the way you think about this is again with your 7 boxes, okay? So we can do a bit of a different variation of a question in a sec. So what you do here is you treat the vowels as a unit, that green unit. So let's do an example where the vowels are the first 2 letters of the word. Well, then you have how many vowels in this word? There's only 2, is I and O. So then it's really 2. Oh, I won't use that color. I'll use green, or sorry, blue. So 2 and 1, okay? So you had 2 vowel options for your first. You used one of them, now you've only 1. And then you have the rest of your consonants here. So it's 5, 4, 3, 2, and 1, okay? Now the idea is they don't have to be there. They can move in. So I'll do one more of these. And again, I'm not going to waste much time on this because I already showed this in the part 1 of the video. They don't have to be the first 2 letters. They could be the second and the third. Okay, so then your 2 and a 1 really goes here. And then how many options are there here for the consonants? There's 5. You've used 1. Now you have 4, 3, 2, and 1. So look at these. These numbers are all identical. Okay, so whatever number you get for this, you'll get the same number for this. So this question is really about you working out how many places can this green box move to. So we showed you it could move to 2 places there. It could also be here. That's 3. It could also be here. That's 4 places. It could also be here, 5, and it could finally be here, 6. So all you got to do is 6 times whatever one of these was here. So if I go 2 by 1, by 5, by 4, by 3, by 2, by 1, I get 240. So the answer is just 6 times 240 because it's either this option or it's this option. So you'd be adding these different scenarios together. So that's why it will be like 240 plus 240 plus 240 plus 246 times. Okay. So yeah, that works out as 1440. Right, let's try and come up with a smarter question here, just for people to give it a go. What if we said the consonants had to occur together? So have a think about that, people. What if the consonants had to be together? So pause the video, give that a go. So if the consonants have to all occur together, okay, so again, 7 boxes to kind of try and visualize it. So the consonants, because there's 5 of them, they come together like a unit of 5 like this, do you see? So this is our consonants, so let's load them in here. I won't use that color, I'll use maybe like pink. So 5, 4, 3, 2, and 1. That's all our consonants loaded into the first 5 letters. And then we have our vowels here, 2 and 1. Great, now let's think about it. Where can the consonants move? They can move as a unit into this slot, or they could move into a unit to this slot. So there's only 3 places they can move, okay? So all we got to do is basically 3 times whatever our answer is for 5 by 4 by 3 by 2 by 1 by 2 by 1. So it'll probably be the same as what I got before there. Something like, I forget the number. By 2 by 1 by 2 by 1. Yeah, it was 240. So there's just 3 different ways we can rearrange them, as you can see with the straight boxes there. So that's the answer to the question if it was all the consonants must be together. Okay, so great. So we learned something new there. Right, I'm going to scroll along anyways and find the next question. Okay, so scroll down there. So I found this here in 2019's official paper too. We're told in independence, so I'm going to get this set up. Obviously, pause the video, give this a go. It's a pretty good question. So what's interesting here is they're actually using this less notation. Do you see this? This means F less S, right? So let me see, can I actually zoom in on that? I want that to be a bit bigger so people can see it very clearly because it's a good question. So that looks like a good size. Okay, so this is not F given S, this is F less S, right? So what that means is it's the probability of F without S's probability. So what you got to do here is you got to look at your f, right? That's all of that is f, and you want to cut out of it everything that's in s. So what part of that red thing is in s? It's this. So you got to subtract that. And when you subtract, that's what the less mean. It's a bit like a subtract. When you subtract that area there in green from the red area, you'd be just left with the quarter. So that's great. They've actually already put that in the diagram for us. They've already put the intersection in as a fifth. Have they put this in first? Let's check. When they say s less f, what they want is to have our s here. Find everything then that's in f and take away from it. So the part of s that's in f will be this. So then basically that just leaves this region here. Okay, that region there that I circled is s less f. It's s without f's part. So that's what, and they labeled it in nicely for us as x. And is this labeled incorrectly for us? It is, because all of this is f union s when you shade it in. So then this dash here means not. So this is everything that's not in the red area that I shaded in there. So hopefully people can realize that this is this region out here. And they labeled that y in the question, and they labeled it y in our Venn diagram. So the great thing is, when you read a question like this and you see that all the information is in on the diagram, you don't need to kind of be rereading this statement up here, except for this one piece of information that isn't in the diagram. If f and s are independent, there is a special formula that works. It's that the probability of f intersect s is simply equal to the probability, you write that as a p, probability of f multiplied by s, probability of s. That formula only works if they're independent. It doesn't always work, but in this question they tell us they're independent, so we will be using this formula. Right, so it says find x and y. So we can actually write down what the probability of f is from our Venn diagram. Probability of f is just everything in this big circle here for f. So it's them two things added together. So it's whatever a quarter plus a fifth is. What is a quarter plus a fifth? Okay, so that's 9. That is 9 over 20. So that's great. We have something. Okay. We can also write down what the probability of s is from our diagram. Let me get another color. Probability of s will be everything in the s circle. So you can see it's a fifth plus x. Okay. So that's great that we have that. So now we can sort of use that information up here. Can you see this? We have probability of f and we have probability of s, and we know f intersection s is a fifth from our diagram. So this should be able to get us x. So then this guy here is a fifth, because that's what he is from the diagram. That's where f intersects s. We just got probability of f. It's this 9 over 20. And then we multiply that by probability of s, which is a fifth, plus x. Great, look at this. One equation, one unknown. We should be able to find x. So what could we do here? Maybe, tricky stuff here. What I'm going to do is a pretty smart thing here. So because this is multiplying this, I'm going to divide both sides by 9 over 20. And if you divide both sides by 9 over 20, it's like multiplying this side by 20 over 9. Okay, so hopefully people get that. So then that would be 20, and then you multiply the bottom by 9, it becomes 45. And then this is just 1/5 plus x. So I hope people got that. That's a pretty slick move there. So if you divide both sides by 9 over 20, it's the same as multiplying both sides by 20 over 9. And that's what 20 over 9 multiplied by the left here gives. And then this disappears. Cool. What does then, yeah, so we get x then. I'll let the calculator do the work there. So what is 20 over 45? Take away a fifth. So x is working out as 11 over 45. Great. So now we can get y pretty simply. So the idea is here, all of those should add up to 1. This is the universal set. They should all add up to 1. So you could say 1 equals this here, which is a quarter, plus the intersection, the fifth, plus the x, plus the y. Now we wouldn't write it as x. We'll write it as what we found it to be, which is 11 over 45. And great. This is one equation, one unknown y, and we can find y. And again, let the calculator do the work. 1 minus 1 over 4 minus 1 over 5 minus 11 over, yeah, so yeah, they're all minus because I'm bringing them over. That makes sense. Yeah, so I'm getting y to be 11 over 36. So hopefully you were able to get them two answers there. It's a pretty good question, that. Absolutely, yeah. It would have been a little bit of a better question if they didn't fill in the diagram at all and they expected the students to correctly place the quarter and the fifth and the x for themselves, okay, and the y. So, but I showed you how to do that with the shading at the beginning. So a great question, I think. Right, I'll pause that, find another one. Yes, so there's this very interesting question from 2018, and we see some unusual notation here with the factorials and n's and stuff, and we're told it can somehow become a cubic. So this is a really good question. It's pretty tough if you've never seen anything like this before. So give it a go. I'm sure some people might just be completely stumped by it, and some people will get kind of fairly decently far in it. So give it a go. So the very first thing you have to understand here is this trick. 7 factorial is obviously this. I'll write it out by hand so you can understand something. Times 2 times 1. Now, look at this. What is, say, this that I'm underlining? That is 6 factorial. So if you wanted, you could write 7 factorial as just the number 7 multiplying 6 factorial, if you wanted. You could also do it this way. You could say, right, what's this? That's 5 factorial. So you could write 7 factorial, if you wanted, as a 7 times a 6, all multiplied by a 5 factorial, right? So you have this option. You can kind of hand multiply certain parts and then just say factorial for the rest. Now this is what's interesting up here. You could take something like n plus 3 factorial, right? And you could start multiplying it back down, right? So that would look like n plus 3 multiplied by n plus 2 multiplied by n plus 1 multiplied by n. Do you see what's going on? I just have to keep multiplying all the way down. Dot, 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 multiplied by 1. It'll go all the way down to 1. But this is what you can do here. This is what's pretty smart. You could, if you wanted, stop, say, here. Leave that alone. What's this I've underlined? Hopefully pause the video, have a think about what this is I've underlined. This is multiplying from n plus 1 all the way down to 1. That is n plus 1 factorial. So if you wanted, you could write n plus 3 factorial as this. An n plus 3 by hand, an n plus 2 by hand, and then multiply by the rest, which is just n plus 1 factorial. And that's basically just that trick up there I showed you in red and green. Now, why is that useful? Because I can take this and I can write it like this in terms of an n plus 1 factorial and then just kind of cross it out with the n plus 1 factorials on the bottom. Okay, so hopefully that makes sense to people. So let me clear this away. So as I said, I'm going to apply that trick here now. I've showed it. You can rewind the video if it's a bit confusing. So I'm going to write n plus 3 factorial as n plus 3 by hand, n plus 2 by hand, and then all multiplied by n plus 1 factorial. Then I'm going to multiply that by n plus 2 factorial, right? But I'm going to rewrite him again like this. I'm going to call him n plus 2 by hand. And then I'm going to say multiply by the rest, which is n plus 1 factorial. So that there in green is this here, that part. And then the part in red is this part here. Okay? And then the reason I've done this, as you can see here, what was always on the bottom, I'll write it in purple, there were n plus 1 factorials on the bottom. N plus 1 factorials. And look at this. That can cancel with that one, and that can cancel with that one. And look at all that's left on top now. All that's left on top is and there's a 1 on the bottom, actually, when they cancel. You're just left with n plus 2 times n plus 2. Okay? All of that there that looked really complicated is actually just this. And if you multiply it out, you're going to get yourself cubic, sorry. So then n plus 3, this is obviously n plus 3 times n plus 2 squared, isn't it? Now we can square that thing out quickly. N plus 3. You square the first term, you multiply it together and double it, 4n, and then square the last term, 4. And then you multiply this out by hand. So the reason I'm not writing an equal sign is because I'll bring the equal sign in at the end. So I'm just kind of reordering it here. So then this will be n cubed, n times 4n plus 4n squared, plus 4n, then the 3's turn now, plus 3n squared, plus 12n, plus 12. Now we'll tidy that up. When I tidy all that up, I'll do it up here maybe in green. When you tidy that up, you get an n cubed. There's a 4n squared and 3n squared, so I see 7n squared there. There's a 4n and a 12n, so I see a 16n. And I see a 12 at the end. And so now we know A, B, and C. A is 1, B is 7, C is 16, and D is 12. So that's a really important skill for people there, learning what you can do with the factorials as I demonstrated there. So hopefully people benefit from that. And if you did, sure, leave a comment saying that was a great thing to learn. Okay, so right, I'll clear this away and I'll get us set up for our next question. Okay, so I have scrolled along here and we're at 2017 mock paper now. So this is a very interesting question that came up with. This is a very smart question. And I also have a note to myself here to show you the rules of combinations after, well, basically before we do the question, just so you can understand them. So let's get this set up here. So to demo the rules of, sure, I'll be demoing that anyways. There's no need to bring that into the question. So obviously, if you can do this, pause the video, give it a go. But I'm going to just show off some important things people should know about combinations, right? So first of all, you've got to know that you can actually do combinations by hand yourself. Right, 7 choose 3, you can actually write that out by hand yourself. You don't need a calculator to do that. You should know what this is on top, it's like you're doing out 7 factorial, but you stop after just 3 units, okay, whatever the number is down there. And then on the bottom here, it actually is 3 factorial. So what I recommend people doing is type that into your calculator and then do 7 choose 3 and you'll be like, huh, that actually is the exact same thing. So in the same way, what's 10 choose 2? Well, 10 choose 2 by hand should be 10 by 9 over 2 by 1. So that's 90 over 2. That's 45. You type 10 choose 2 in your calculator, you'll get 45. So you're like, oh, this works. This is pretty cool. And it is pretty cool. So hopefully people get that. I'll do one more just so you can see it. 10 choose 4. That will be 10 times 9 times 8 times 7, and you stop, and then it's over 4 factorial. And type that into your calculator by hand, the 4 things multiplying on top and bottom, and you see it's the exact same number as 10 choose 4. Great. If you didn't know that, make a note on it. It's fantastic knowledge. Okay, so we've got to know as well when we see like 7 choose 1, 10 choose 1, and what 9 choose 1 is, okay? Anytime it's choose 1 on the bottom like this, the answer itself is just like 7. It's just like 10, and it's just like 9. So n choose 1 itself is just n. That's a really important thing you're meant to know. N choose 1 is n. You could prove this to yourself here as well. You could just, what this would really be would be a 7 times itself on top, and then it'd be a 1 factorial on the bottom. So that you should be pretty at peace with this. But the idea is you need to know this choose 1 thing. Right? Another thing you've got to know is if you have 7 choose 0, 5 choose 0, 10 choose 0. All of those are equal to 1. Okay, anything choose 0 is 1. Let me kind of try and put this into words for you. The reason 7 choose 1 is 7 is because what this is really asking is there are 7 people. How many ways are there to choose 1 from 7 people? Well, there's 7 ways. You just pick everyone individually once, if that makes sense. Why is 7 choose 0 1? It's asking how many ways are there to pick 0 people from 7? There's only one way. You don't pick anyone. Okay, so hopefully that makes sense. But anyways, the idea is here that n choose 0 you've got to know is 1. Okay, pretty big thing. Now, there's this thing called the mirrors, right? So one other thing I'll just show actually is if you had 7 choose 7 before I show you the mirror thing. 10 choose 10, and then let's say you had 5 choose 5, and then work them out in your calculator and tell me what you think n choose n is. Okay, so you should all get 1 for them. And the reason they're 1 is, think about it, it's like, how many ways are there to choose 7 people from 7? There's only one way, you pick them all, that kind of thing. So n choose n you got to know is 1, right? Now we're going to get into this thing called the mirrors. So it turns out, work out that, and then also work out this. Then work out 10 choose 3, and work out 10 choose 7, okay? You should start to see what's happening here. Work out, say 10 choose 1, and work out 10 choose 9. Work out 5 choose 0, and work out 5 choose 5. What did you notice? All of them are the exact same, okay? Not as in like all of them are giving the same value, but as in 7 choose 2 has the exact same value as 7 choose 5. 10 choose 3 has the same value as 10 choose 7. 5 choose 0 has the same value as 5 choose 5. So these are like mirrors of one another. You see how like the 1 and the 9 are mirrored like with the 10, if that makes sense. So if this is 0, this has to be 5 if you want to get the opposite. So I'll give you an example of this. Let's say you had 15, like in this question. Let's say you had 15 choose 2. Who would he be the mirror of? So hopefully you realize that should give the exact same value as 15 choose 13, because you know the 2 and the 13 add to give the 15. That's the kind of mirror effect. And you can confirm that in your calculator. Great. So that's pretty much the rules of the combinations, okay? And obviously a really big thing you've got to know is like, say you had 15 choose 3, you can do that by hand. It's just 15 by 14 by 13 over 3 factorial, 3 by 2 by 1, okay? So really important stuff. I hope people remember that and learn that, okay? Okay, so let's do this pretty important thing here. I'm actually going to make a note to myself to cut that part out of the video and make a little short video for people, just in case people don't watch the full video and see that really important thing I showed there. Let me pause the video and make a note for myself. Okay, so I made a note there, so that what I demonstrated to you there will be made into like a short little like 10-minute or whatever 7-minute video on the channel, because it's pretty cool stuff, as you'll imagine. Okay, so we have to somehow do this here. So the idea is we're going to use the mirror effect here, right? It's a little complicated. So as we said, if this was 15 choose 2, we know its equal would be 15 choose 13. In our heads, where did we get the 13 from? Think about it, people. Where did we come up with the fact that this is 13? What we actually done in our heads was we went like 15 minus 2. Does that make sense? We took 2 away from 15 and then we came up with a 13. So that's the exact same logic here. This number, if we didn't know what it was, what we'd say is, oh, well, the number that should go there is this number take away 15. Because that's what you did there in your head. If you wrote 13 here, you went 15 minus 2, and then you wrote 13. So in the exact same way, if you didn't know what number was here, you'd go, oh, it's just 15 take away this number. So that's what you do here. You go 15 minus or plus 3, and that will give that number I've shaded in there. But that number actually has a name in this question. It's called 4or minus 13. So this was a really smart puzzle this year for students. So yeah, as obviously we have one equation here now, one unknown, so we can move it around, find or. So you get 15 minus or minus 3 equals 4or minus 13. Bring all the ors to one side, so I'm seeing a 5 or on its own. I'm seeing a 13 come over. That'll be a plus 13, then that's plus 10, maybe 25, if I think it's right. And then or is 5. You can actually test if this is correct in this question. So I'm getting or to be 5 there anyways. So when you sub it back in, it's really asking, is 15 choose 8 equal to 15 choose, right, what's 4 by 5? It's 20. 20 take away 13 is 7. Ooh, and they are indeed a mirror of one another. So this is correct. Okay, really cool question, and hopefully you learned a lot there from the combinations. So what I'm going to do here is clear this away, and then we'll move on to our next question. Okay, so I scrolled along there, and I'm seeing that our next question comes from 2017. Now this is a really important question, because we'll obviously fill this in because we'll need it, but this isn't the question that I'm actually interested in doing. It's this down here, okay? It's this really important question. This actually repeats quite a bit. It'll always be the same style of thing. You'll have a big table like this, and you'll have to kind of work back to some unusual given probability, like find the probability that it rained in the morning given that you're late for school. And you got to know how to do that, okay? Because that kind of question is really tough and it repeats itself. And so yeah, so what I'm going to do here is I'm actually, because this video here is on 48 minutes, I'm going to end this part here, and then we're going to come back for another part, and we're going to actually resume it from here, because it's a pretty important question, okay? So I'm going to stop the video. Thanks for watching. Okay, so we're back for part 4 of important past paper questions you should know on the topic of probability. So let's get straight into this. So this is a really important question. So we're going to extract this information, complete a tree diagram on it, and then we're going to answer a particularly tough question based on the tree diagram down here. So obviously we need to fill out this table. I'm trying to think what's maybe the best way to do this so that you can have a go on it. Let me see, can I line this up? Pretty close. Okay, so it's pretty tight. Okay, so obviously pause the video. Hopefully everyone can kind of read that there, and they can give a go at it. Grant. Okay, so uh, hopefully you've had a go at trying to fill that out. So I'm going to put it together here first. Okay, so it says in Galway, rain falls in the morning on 1/3 of the school days. So that's why they put a third here, right? So then this means 2/3 of the time there's no rain. Okay, so the or. So what you do is you kind of list the outcome at the end, and then you write the probability along the tree branch. Happy days. Right. When it is raining, that's we've got to here. The probability of heavy traffic, T for heavy traffic, is a half. So that means there's also a half here for no heavy traffic, okay? And then when it is not raining, the probability of heavy traffic is 1/4. So this is the no raining heavy traffic quarter. So then it's 3/4 here. Okay, so let me try and make that a bit bigger. Quarters. It's just, I know it's a bit small, but it's just the way it is. There's a lot going on here, you know. Keep it going here. When it is raining and there is heavy traffic, so that means when you get and, you've multiplied your way along the branches. So we're here. It's raining and there's heavy traffic. There is a half a chance of you being late for school, L mean late. Okay, so then that means there's a half a chance of not being late. Okay. When it is not raining, okay, not raining, and there is no heavy traffic, okay, that's probably down here. The probability of being late is 1/8, so that's how they wrote the 8 there. So thankfully they've kind of put some of these statements in the diagram. So then you have a 7/8 chance here of not being late. So I wish I had a bit more room here. I suppose I can start writing down there. Okay, so that's 7/8. There's one more here. In any other situation, the probability of being late for school is 1/5. Right. So in any other situation, so they helped us here a lot. They actually wrote one of the 1/5s here to show us how it would go down. So then that means that's 4/5 there. And then this will also be the same thing. This is another situation. That's 4/5, 1/5, and then this is a 4/5. Right, so we filled out the hard part, I'd say. So what we do then is to get the number at the end, is we multiply our way along the branches to get to this location. And we know we've done it right if they all add up to 1. So let's multiply our way along to get to this L. We go 1/3 by a half by a half. In your head, you should know that that's 1/12. Then we get to this place here, so that goes 1/3 by a half. You shoot down here to a half. So again, that's a 12th. How do we land in here? You have to do this turn here. So you go 1/3 by a half by a fifth. In our heads, that's kind of like 1/30. And then what do we got here? To get down to here, so you got to turn in here. So you multiply your way through. What am I getting? 1/6 times 4/5. So that's 4/30. Yep, 4/30. Okay, so I think you're getting the idea. I'll just finish this out. It'll be just quick. Me finish it out, then pausing the video. 2/3 by a quarter by a fifth. That's 20. So that's 2/60. 2/60. No need to kind of tidy them up. This, it's nearly better write them like this. It shows where your workings come from for the multiplications, because your final answer here isn't to kind of simplify all these out. Our final answer will be more so the part 2 and the part 3. But if this was your state exam, you could write another equals here with the simplifications for them. Particularly like say this one here, you'd write that as 1/30. Okay. Anyways, 2/3 by a quarter by 4/5. So that's going to be 8/60. 8/60. Down to here then. 2/3 by this by an eighth. That's a tricky one. So then that's like 12 by 8. I think that's 96 on the bottom. And then it's 6/96. And finally, the last one. Again, it's a 12 by 8. So it's 96 on the bottom, but then it's 6 by 7, which is 42. So this is like 42/96. Now I can know if I've done all them right. I'm going to type all them into a calculator, make sure they work. So again, it's probably just as quick as me type it in now than pausing the video and typing it in. So 4/30. plus 2 over 60 plus 8 over 60 plus 6, I'll just call it 48 over 96. Yeah, well that's 1, so I know this is 100% correct. Right, what I'm going to do is I'm going to take a snip of this so I can bring it along with us. Okay, great, and then I can clear this away. Great, so that's there for us to kind of study. So what we're really after is to be able to answer these questions here. So let's zoom in. So obviously pause the video and give these a go, guys. So based on using this, is there any nice way I can get this lined up here? Yeah, that's not too bad. That's actually not too bad. So pause the video and give this a go, see what you can get out. And let me see, I'll have a pause here, see can I set this up any better. If not, I'll just sort of leave it the same. Yeah, no, this works anyways for how simple this part 2 is. I'll try and rejig it for the part 3, okay? So anyways, on a random school day, find the probability of being late for school. It's pretty straightforward. So these are the scenarios where you're late for school, right? So then you just add them up. You can be late this way, or you can be late this way, or you can be late this way, or you can be late this way. So then you could just write the probability of being late, P of L, is just equal to a 12th plus a 30th plus 2 over 60 and then plus 6 over 96. Right, let me type that in here and see what we get. 1 over 12, 1 over 30 plus 2 over 60 and then plus 6 over 96. Okay, so that's working out at about 17 over 80. Okay, 17 over 80. Right, I'll make some room now for the next part. So let me pause and make some room. Okay, so I've set that up for us now. So obviously give this a go, pause the video and try it. This is a really, really good question. This kind of thing repeats, okay? So we gotta know how to do this. Right, first of all, to get some marks, even getting this question off the ground, you need to understand what they're looking for. What they want from us is to find the probability that it rained given you were late for school. Now you gotta convert that into a given probability statement. What they are asking for of you is, let me use a color like green. They're asking for the probability that it rained given, straight line, you were late for school. Okay, that's your question mark. You're looking for this. If you get this, it's actually always good to use a question mark. If you get that, you get the answer, okay? You're looking for that. Rained given you were late for school. So the way to do this, using our given probability formula, is R given L can be expanded out to be the two things intersecting. Let me try and write this neatly. Or intersect L divided by the last thing mentioned, which is the probability of being late. Now, this is great because you think about what was part 2. Part 2 actually had us work out the probability of being late. Do we remember that? What the probability of being late was? It was when we added this to this to this to this. That was the probability of being late, right? So now there's this tricky bit, right? So we know what the thing is on the bottom. We just worked that out. You need to think now, what is the probability of it raining and intersect means and it being late. So hopefully you've given this a go and you've realized what it is. The rained and being late are just these scenarios because this comes from the rained area to get in here, okay? So that's what this question is. This kind of question repeats, right? What they're getting you to do here, and I can write it out by longhand here, this is equal here, probability of R given L. They want you to get some specific scenarios of raining intersect being late. Take those specific scenarios and then divide it by all the scenarios of being late, for example. So that's what this is. And this literally, if you do enough past paper questions, you'll see this type of question repeats. So what this is here, it's just the 1 over 12 plus the 1 over 30, because they're the scenarios when you were late and it rained, the intersection. And then we divide this by the probability of being late, which we worked out in the last question. But I'm going to write it out longhand again here because of just, it's nice to see written out like this. 2 over 60 plus 6 over 96. So a really important question. Trust me, if you do enough past paper questions, you'll see that this really tough kind of last part of a question with a tree diagram can appear where it's an unusual given probability. And you gotta know that it's going to visually be like something like this on your diagram, where you'll take out some specific scenarios and divide them by a larger amount of scenarios like those in green. So it's pink over green here, really. Grant, I'll Sure, I'll type that into calculator. It's not going to take me too long. 1 over plus 1 over 30 plus 1 over 12. 1 over 30 plus 2 over 60 plus 6 over 96. So if you do that, you should get the answer to this question is 28 over 51. Okay, great. Really good question. Make some notes on it if you got stuck with it. And if you got it out, well done. All right, let me clear this away, get on to our next question. Okay, great. So I've scrolled on to our next question here, an interesting one with these marbles. This comes from a 2016 mock. Okay, so let's get this set up. Obviously, people should pause the video, give it a go themselves, see can they get out the answer here. So what are they looking for us here? I could probably zoom in a little bit on that as well too. It doesn't have to be so small. Right, so hopefully you've given it a go. Bag contains 3 red marbles, 4 blue marbles, and X green marbles. Okay, so in the bag there's like 7 plus X marbles, right? Given the probability of choosing 2 greens is 5 over 26, calculate the number of marbles in the bag. Right, this is pretty easy. So if you want to draw a green, right? Let's draw a green. There are X greens in the bag divided by the total number of marbles in the bag. So that's 7 plus X. That's how the probability of drawing a green, right? And we need to draw another green. So okay, how many greens are left in the bag? There's X minus 1 greens left in the bag. Okay, think about that. And then how many is left in the total bag? Will it be 6 plus X? Okay, so hopefully that makes sense to people. Originally there's X greens, you take one out, there's only X minus 1 left. There was 7 plus X marbles, you take one out, then it's 6 plus X. Okay, and then they say that's equal to 5 over 26. Now, so let's have a study of what we have. We have one equation with how many unknowns? 1, X. So it's a game of algebra now. Okay, so this was an interesting question for how it worked out. So then you get X squared minus X. You should know how to multiply that out on the bottom quickly. It just comes like X squared, 13X, and then 7 by a 6 is 42. And then this is a 5 over 26. Cross multiply. I can do it down here. 26x squared minus 26x equals 5x squared plus 13 by 5 in your head, 65. And then 5 by 420, that's 210. You should know how to do them in your head if you don't. So you just like multiply it by 10 and half it. That's what multiplying by 5 does. So I go 130 divided by 2, I get 65. I go this by 10 gives 420, divided by 2, you get 210. That's what 5 multiplying by 5 does. Okay, so bringing them all over to the one side. Bring them all over to the left. 21x squared minus 26 minus 65. That'll be minus 91. Minus 91x, yep. And then bring the 210 over, minus 210, and then that's equal to 0. Now this probably can be factorized, but I'm not too bothered with that. I'm just going to use the, because 91 looks a bit awkward. I'm just going to use the minus b formula here. So then this will be minus b plus and minus the square root of 91 squared. Again, the sign doesn't matter because you're squaring it. Then it's minus 4 bracket a, which is 21, times c, which is minus 210. So all of that will turn to a positive, all over 2 times 21. You type that into your calculator. So I'll pause the video for this. Okay, so when you do it with the plus, you get x is 6, and when you do it with the minus, you get x is minus 5 over 3. Now, how could x be negative? You can't. It's the number of green marbles in the bag, so the answer has to be 6, right? And it's a little bit of an annoying question here. I don't know would they really do this anymore. It's like, what were the number of marbles in the bag? So technically, you get deducted a mark if you think that was all you had to do. You had to work out the total number of marbles in the bag. So you wouldn't just write 6, you'd write 7 plus 6. So there's 13 marbles in the bag. Okay, but that's that's whatever. Right, I'll clear this away, get us our next question. Okay, so I've scrolled on to our next question here. It comes from 2016 mock paper 2. So we'll hammer this out here. So what do we got? Let's read through it and obviously give it a go yourselves. So the attendance of a GAA match depends on the weather, as you'd imagine. The probability of a large crowd attending, okay, so we'd probably call the large crowd L. Probability of a large crowd attending is 0.9. The probability of a large crowd attending, if it is raining, so that means given it's raining, is this. Okay. Probability of a large crowd given it's raining is 0.3. The probability of it raining on match day is 0.2. Okay, so that's the probability of it raining is 0.2. Right? Calculate, this is what is going to be the question mark. Calculate the probability of a large crowd attending given it is raining. That's the question mark. Now, looking at this now, I don't know, did they intend this? But they basically just, actually, they've already given us that thing. Okay, so the answer is 0.3. So I'm very suspicious that this question has a typo in it, and that's not actually what they wanted us to get, you know. Um, so obviously, you know, this wouldn't happen in an official state exam, and it's very unlikely they just wanted students to read the question carefully and see it's given. Maybe they did, um, but we might try and get something else here to maybe learn something from this question. So let's say they asked you for something like probability of or given L, okay? Let's say this was the question mark, not something that was already contained in the question. So maybe pause the video and give a go at trying to get that, okay, so that this question isn't completely busted. Right, so hopefully you realize that this is what we're looking for, so we might go and pull that thing apart using our usual knowledge that or given L is equal to the intersection of the two guys divided by the last thing mentioned, which is probability of L. Now we have probability of L. We don't have this thing. So remember, we're looking for this here on purpose. So we don't have this thing. But we have this probability of raining, which we haven't used yet. So what we could do is we could use the other version of this here, where we expand out L given or, right? So we go probability of L given or. The expansion of that then is the two guys intersecting, L intersect or, over probability of or, right? So what do we see here? So we know this guy's value, it's 0.3, and we know this guy's value, it's 0.2. So then we can get the intersections value, okay? So hopefully you can see that. So probability of L intersect or would be equal to probability of or multiplied by probability of L given or, and that's 0.3 times 0.2. And that in your head or with a calculator should work out as 0.06. So now we've got L intersect or, but as I've been saying to you, L intersect or is the exact same thing as or intersect L. So we have that. And actually we already have probability of L, so this question should be solved. So it should be 0.06 over 0.9, and whatever that works out there in your calculator to be. 0.09 divided by 0.9. So I'm getting a 15th for that. It's probably the cleanest way to write it. Yeah, so it's hard to know what they were looking for there in that question, but at least we've done something and learned something by making up a purple question here. Okay, cool. I'll clear this away and then move us on to our next question. Great, so we're back here now. So I've got us another question here, and this is on this is part of a bigger question here. So this is part D. So we're not going to do this whole question. So this is on the basketball player here named Michael. So what we're going to do is I'll take a snip here of this here, okay, because we'll need this to kind of think through this part of this question here. So you don't need to do the previous parts, but just in case anyone wants to give them a go, they're there. You pause the video and look at them. But yeah, what I'm interested in is getting people to try these two parts out here, okay? So let's see, can I make that a bit smaller? Scroll down, now you can see the two parts. So I'll have a pause of the video, everyone, and see can you hammer these out, okay? So let's see what's going on here. Let P of n be the probability that Michael is successful on his nth free throw in the game, right? And then obviously 1 minus Pn is unsuccessful miss on the nth free throw. So when we're talking about the nth free throw, we're like, say he's taken like 100 shots. We're way into the game kind of a thing. The nth throw. That's kind of what's maybe implied here. Or, you know, n could be, you know, very small as well. They don't, I suppose, make that statement. It's down here when they say the long run thing, so for large values of n. So they don't really make that statement yet up here in D part 1. Anyways, so he's a basketball player, and his very first shot has a chance of 0.7 of going in. But things are very dependent here. Okay, this is not a Bernoulli trial. This is where, uh, yes, there are two outcomes, success and failure, but they are not constant in their values. So if he scores, his next shot is a zero point 0.8 chance of going in, or if he misses, it's a zero point 0.6 chance of going in, and so on and so forth. So that's every next shot chances of scoring depends on what happened the previous shot, and that dependence makes you not a Bernoulli trial. Okay. Anyways, so we've just somehow come up with this. This is a little bit complicated. It would be seriously hard to come up with this. They didn't tell us what we're trying to get. Okay. So we're looking for the probability that he scores on his next shot, and we're told that Pn is the probability that he scored on the end shot. Does that make sense? So n plus 1 is the next shot after the end shot. So hopefully, as I said, it is tough this. But the chance of scoring on his next shot depends on what he done on the last shot, right? So he could have done two things. He could have scored on his last shot. Now, scoring on his last shot is a probability of Pn. Now, if he scores on his last shot, the chance of scoring on this shot is 0.8. So we'd multiply that there by 0.8. So the reason we multiply is because we're looking at the chance of scoring on his next shot. A way of doing that is you score before and you score again. Okay, hopefully that makes sense to people. Or, there's another way of doing this. Let's say he missed on his previous shot. He missed on the end shot, and we said the probability of missing on that shot is 1 minus Pn. Now, if you have missed, Michael's chance of scoring now on this n plus 1 shot is 0.6 because he missed his last shot. Okay, hopefully that makes sense. You could write this out for yourself. There's two ways you can score on this shot. You can score, and then you can score again, or you can miss. So you can write it as or. You could score, or you could miss score. That's the two ways of scoring on the n plus 1 shot, taking into account what happened the previous shot. Okay, hopefully people are okay with that. As I said, it's quite tough to think through that, but you got this kind of hint here, so you can kind of jig this together anyways if you were stumped in an exam. So you can see when you multiply this together, you get the Pn, and then you get a 0.6, and then it's a minus 0.6 Pn, and there you go. You see when they take away, you'll get the 0.2 Pn, and there's your 0.6. Happy days. Great, so we have that formula from up there. Now assume that P is Michael's success in the very long run. That means he's been shooting for ages, right? And we can assume this. Now this is a mathematical instruction. We're being told to do something here. We're being told to replace this thing here with P, and we're being told to replace this thing with P. You see? So you're just following the instructions here. Approximately equal. For the maths, we're going to set them basically in as P, right? And then it goes then show that P is this. Again, this will be a tough question if they didn't give us what we're looking for. But it's quite generous this because we know what we're trying to manufacture here, you know? Anyways, we'll put a P in there. And it's equal to 0.6 plus 0.2p. Bring this over, you'll get 0.8p when you take it away, and you get 0.6. And we should be able to do what 0.6 over 0.8 is in our head. That's 3/4, and 3/4 is 0.75. So I picked that one out because I think it's quite a smart question, you know. So yeah, his success in the long run is, if we don't know what happened the previous shot, it's 0.75. But yeah, we'll go with that. Okay. So we'll scroll on down here. That's an interesting question. It's a bit tough. That's more of a patterns and sequences question. So that's not why we're not doing that there. It's not so much probabilities, it's patterns and sequences. And then this is tied in with patterns and sequences and a bit of algebra on inequalities. Anyway, so this is another probability thing here. You arrive at a game. Obviously, pause the video, give it a go. You arrive at a game in which Michael is playing. You know that he has already taken many free throws. So that means that ties in with what we had there before, you know. Remember where we showed that if he's taken many free throws, we can assume that the chance of him scoring here in his next show, the PN is like 0.75, you know. It's approximately equal to this, you know, PN, which was 0.75. Okay. But you do not know what pattern of success he has. In other words, you don't know whether he scored or missed on the previous shot, right? So we'd need to know what he done in the previous shot to take into account. Is he going to have a 0.8 chance of scoring if he scored before, or is it going to be a 0.6 because he missed before? So we don't know. So our best guess at this is what we just worked out there. It's the 0.75, you know. because that's his chance of what is your estimate of him being successful on this next free throw, and that's tied in with what we showed there before, and they give a hint that it's tied in when they say that where was it here? You're at a game, you already know he's taken many free throws, so that's like where the n is quite large, n is big. I'll show you a way to write n is big. You draw two greater than symbols to zero. That just means n is big. Okay. Hopefully, hopefully that makes sense to people. And then down here, part two, why is it not appropriate to consider his following free throws as Bernoulli tries? Because it's just not. That's what this question is about. It's that, okay, let's say Michael scored that first free throw when he arrived at the game. Well, then Michael's next free throw is a 0.8 chance of going in, okay? Because this still is valid. This hasn't gone away up here, okay? Um, and then obviously, if this was unsuccessful, his chance of going in the next would be 0.6. So the dependence is still there. Success and failure are not constant, okay? So that's kind of why. Why is it not appropriate here? It's because success and failure is not constant. If he scores this shot, his subsequent free throws still depend on whether he scored just before, as in the chance of scoring can jump between 0.8 and 0.6, okay? So hopefully people get that. But yeah, it's a little bit of a funny question what they're asking here, where it's like somehow his probability scoring is 0.75 up there, but that's only because we don't know his pattern of success, okay? Realistically, Michael's chance of scoring every single time, he either has an 80% chance or a 60% chance. And which one of these it is depends on knowing what he'd done just before. And if we don't know what he'd done just before, as in we arrive at the game, our best guess was the 0.75 based on what we worked out there before. Okay, a little bit of an interesting question, but I think this part two was pretty important based on what I just started discussing when I talked about this question first, that there is a dependence. What he does before affects what he does next in terms of chance of it happening. Okay, that's not Bernoulli trial. Okay, right, I'll pause this, get our next question. Okay, so I scrolled on down there and I found where I put my next mark for our next question. So you can see two marks here. Look, you might think what this is why I said, remember a question I done earlier on, I think it was someone about it raining and being late for school. You might remember that. So this is like that again here. See, it's a tree diagram and then there'll be a spicy question at the end where it's something given. This is a repetition. What is the probability that the person actually has the disease? Calculate the probability the person selected random test positive for the disease. Okay, so they haven't really asked the given thing there. Okay, but we can tie it in here and is. So this is a kind of another variation of this, you could say. Right, so let me maybe zoom out a little bit so see can I get the whole thing in. I somewhat can. Okay, so we have the whole question there. So obviously pause this, give it a go yourself, see how you get on. So blood tests are sometimes used to indicate if a person has a particular disease. Sometimes such a test gives an incorrect result, right? So you can get these kind of false positives, false negatives, they call them sometimes. Either indicating the person has the disease when they do not, called a false positive, or indicating they do not have the disease when they actually do, so it's called a false negative. Very complicated language there. That's kind of the thing you'd sit down and think about in the exam, okay? But let's see, can we fill in our table anyways? It is estimated that 0.3% of the population have this disease. So you see this here, they've already filled that in for us, which is nice. So then we know this has to be 0.997, okay? You can take it away from 1. Great, we'll keep reading. A test developed to detect the disease gives a false positive 4% of the tests and a false negative 1% of the tests. Right, so we need to somehow get that in their diagram. They've probably put the 1% in, but we have to put the 4% in for ourselves. Person is picked at random and is tested for disease. Okay, so then write down the probability in the boxes. Right, so this is a little bit tricky. So if they have the disease, they should test positive. That's the whole point of the test, right? But you can get this thing called, what's this here? So a false negative, right? This false negative, where you're getting a negative, but you shouldn't. So that's that 0.01 there. So then there's this here with a false positive. So if you do not have the disease, you should test negative. And then you can get this false positive, this incorrect thing here, which is the 0.4 there. So hopefully people understand that. That was a bit tricky. You'd want to sit with that and think about it. Okay, so then that means this here would be 0.96 because there's only two outcomes here you can shoot off. They must add to 1, so that's 0.96. 0.01, so then this is 0.99. So a little bit of a tricky one, that. And then obviously we'll multiply our way along the branches here. So to get out to here, this is probably going to have some seriously annoying decimals. 0.03 multiplied by 0.99. So yeah, it does. It has pretty horrific decimals. So I'm actually going to write it as a fraction. So that's 297 over 100,000. Yeah, 100,000. Okay, and then this one here, you multiply your way along. So it's 0.03 to 0.01. 0.03 by 0.01. So then this is 3 over 100,000. So again, if you're getting messy decimals, I don't know, would they be giving you something with messy decimals in exam? They want people to not be messed up by weird numbers, you know, to be still able to answer the question. So you multiply from here into here to get into here, and I'm getting 997 over 25,000. And then the final one here, this will be a biggish number. It's 997 multiplied by 0.96. I get myself 2991 over 3125. Now, how do you check if you've done that right? Well, there's only 4 outcomes this test can have, 4 possible scenarios. So you can be this, or this, or this. All of them should add up to be 1. Okay, so you can just type that into your calculator there. I'm going to pause and just add them up. I know, I'll type it in here. It'll only take a second. 100,000 plus 3 over 100,000 plus 997 over 25,000, and then plus 2991 over 3125. Ooh, so that doesn't become 1. Something's wrong here. Let me see. What have I done wrong there? Have I typed? Oh, that I've put that in as 250,000 when it's 25,000. That's me rushing. Yeah, if you type them in, you do get 1. Okay, so you know that I filled them out right when you get the 1. So it's a nice thing to check in the exam for yourself. All right, part 2 here. Hence or otherwise, calculate the probability that a person selected at random from the population tests positive. So these are our positive testers here. You just add them together. So the probability of a positive test, probability of P, you could say. It's a bit annoying, the P probability P. So that's just really 297 over 100,000 plus you'd want to show the workings like this for the examiner, you know. Okay, and that works out as 297 over 100,000 and then plus 997 over 25k. I'll type it in right now. It's 25k. So that works out as, it's neater as a fraction, 857 over 20,000. Right, let me see, do I have to clear that away and make room for this down here? And then it says, give this correct 3 significant figures. Okay, so let me see, can I make room? And if not, we'll just hammer this out. So let me pause. Yeah, no, I've decided now there's probably, it'd be just too messy to try and get rid of it. I want to keep all the info on the page as much as possible. So anyways, we're going to read the part 3 here. A person tests positive for the disease, right? So that's kind of a given in a way. Person tests positive for the disease. What is the probability that the person actually has the disease? Okay. So this is what I'm on about actually. This when I read this first, I didn't see this because I was rushing through it. But this actually is similar to what I done earlier on with the person with the car getting to school or something in the late. Remember the rain and the late. So this is a carbon copy of that. And as I said, these repeat, and that's literally what this is here. So you've completed, as you've seen here, a tree diagram, and then they'll ask one of these weird given probability questions. So what they'll say is, what they're saying here is, we're looking for the probability of something. You know, given a person tests positive for the disease. So that's actually given that they've tested positive, okay? Given that they've tested positive. What is the probability that the person actually has the disease? So what we're really asking for, what's the probability you have the disease given you've tested positive? So you had to break down that statement and realize that this is your question mark, okay? And that ties in with what we've done before with the late and the raining. So what we do with this is we write out what it is. It's D given P is equal to the intersection of the two guys, disease intersect test positive, over divided by the last thing mentioned. And this is, as I said, pretty much a carbon copy of the question we've done before. It's going to be a very specific scenario. of where the person tests positive for the disease. So let me clear this out here. And they actually have the disease. So that is, you have the disease and you test positive. So that is this specific scenario. And we're going to divide that then by all the scenarios of where you test positive. And so that's that one, and then that's that one. So you see what I mean? It's you take one scenario and divide it by multiple scenarios. And that's how these questions go down. So they are a bit of a repeat thing, okay? So I've written that not really great, so let me try and make this line. D given P will be equal to the intersection here, so I'll keep the colors going. So I said the intersection was that one up there, so it's the 297 over the 100,000. That's the only scenario. And then it's over the probability of testing positive. And see the hint, we actually done this in part 2. That was very similar to the raining and the being late one. You can rewind the video and you'll see that they actually made us work that out in the previous part. So that's that number. But again, rather than writing it in, I'll write it out by hand like this so you can see the two. So you and the examiner can see the two things. 997 over the 25,000. Great. And so that then as an answer works out as, now I have to give, I'll write it as a fraction first. And then I'm going to write it to the three significant figures. That's a kind of good practice habit. 297 over 100,000 plus 997 over 25,000. So tough question this. So this here works out, I'll write it in red maybe. Yeah, you can see this. So 297 over 4285, right? I'd write that first, and then I'd write that this is equal to, give your answer correct to three significant figures. So what this means is, when I type this out, this is 0.0693, and I'd stop there. So this is 4 decimal places, but this is 3 significant figures. And anyone who's not comfortable with what the difference between significant figures is and decimal places, I highly recommend looking up a video on YouTube, just maybe like a YouTube short, and they'll show you how it works, okay? Something you should know, small little thing to know. Anyway, so that's the answer there. And as you can see, what I meant, that is literally a repeat of how the question for the being late and the raining worked at the beginning of this part in the video. Okay, great. So you usually take one specific scenario and divide it by multiple scenarios like this to get this given thing. Okay, right, I'll clear this away and get us set up for our next question. Shouldn't be too many left. Okay, so I scroll along here and we've got to this 2013 question. Now, this is very unusual. You wouldn't see something like this that often, but it's so unusual that it'd be nice to ask and just see, do students know this, you know, in a state exam nowadays, because it's pretty important they do know these things, obviously. So we're being asked, what is a sample space? And you get something like 5 marks for this, 5 marks for this, 5 marks for this. These two are pretty important to see, can the students explain these? The sample space is a little bit of a curveball. So a sample space, you should know, is a list of all possible outcomes. Right, where would we see a sample space? I'll show you a sample space now. Let's say we have a coin, right? Let's say we have a euro coin, and let's say we have a dice. Look at me here drawing the stuff. Okay, so how many outcomes are there here that can come? So you should know there's 12 outcomes. You can have head or tail here, right? This thing has head or tail, and then this thing has 1 to 6, doesn't it? So there's 6 outcomes there. So there are 12 possible outcomes because you get a result here and a result here. So you multiply them together. This is like the box method, you know, when you have the boxes and you times them together. How would you create the sample space if you were asked? You'd make a little table like this. Okay, this is important for people. Yeah, I got it there. So this could be like your head and your tail, and this is the 1, 2, 3, 4, 5, and 6. So then this will be H1, H2, H3, H4. Do you see what I mean? H5, and then I'll do some down here. This would be T4, T5, and T6. How many boxes are there? There's 12. Okay, so that means there's 12 possible outcomes, but the sample space is this thing here. It is the list of all possible outcomes like this. That's T1, T2, T3. So that is a sample space. Okay, list of all possible outcomes. Great. Right, mutually exclusive events. So you should know this. Mutually exclusive events, it'd be nice to do a diagram here for the examiner. So that's what mutually exclusive, that diagram tells the whole story. It's that they don't, in words, they don't occur together. A and B can't occur at the same time. In other words, what is their intersection equal to? It's equal to 0. And the word mutually exclusive, mutually means it's like an agreement. They agree to exclude one another. In other words, they're excluding one another here. Okay. Great. Now, independent events. This is an interesting one. So if they're independent, right, it means one event happening does not affect the chance of another event happening or not. So that would get you full marks there. Okay. In other words, like it raining in Los Angeles does not affect whether or not I'm going to get a head or a tail on a coin here in Ireland. That's just not what's going to work, okay? Like, as in, they're completely independent of one another. It raining in Los Angeles does not affect whether the probability of me getting a heads on a coin toss here, okay? So that's an example. One event happening doesn't affect the other. Whereas I'll give you an example of dependent events. So that would be like, say it rains here and the chance of me wearing a coat. If it rains, I'm more likely to wear the coat. They're clearly dependent. One event happening changes the chance of the next event happening. Right. For us here, a nice way to write this down as well as the all-important formula. If events are independent, the intersection of them equals their multiplication. That formula only works if they're independent. So you'd want to give the worded explanation I've been giving you there. If one event happens, it doesn't change the likelihood of the other event happening. That's independence. And then also state this formula. One other important thing you should know is where this formula actually comes from. Okay, so this is a kind of a flashcard thing if you didn't know this. Right, if events are independent, right, we know this formula always, this is always equal to their intersection divided by the last thing mentioned, right? We know that formula always works, right? Now, I'm going to ask you a specific scenario. This works whether they're independent or dependent, right? That formula always works. I'm asking you a very specific question now. If A and B are independent, right? They're independent. In other words, A happening isn't affected by B happening. Pause the video and tell me what you think the probability of A given B has occurred is if they're independent. So hopefully you realized if B occurs, A does not care. It does not affect A's chance of happening. If B occurs, they're independent, so B can happen and it will not change as A's probability of happening. So this is actually just equal to the probability of A. Think about it. B happening, it doesn't matter that B has happened, or even if B has not happened, B not happening, that's what the not means. It's still probability of A because they're independent. So this up here, that in pink, this is only true if A and B are independent. Hopefully that makes sense to people. So look at this now. Look at this, right? If they're independent, well then you can sub this here in for this here. So then in an independent scenario, that becomes probability of A. Oh, and look what happens. You multiply across by probability of B, and then you get probability of A times probability of B is equal to the intersection. And ta-da, that's where that formula comes from. It comes from this understanding up here. Okay, and obviously as well too, B given A has to be equal to the probability of B if A and B are independent. A happening does not change the chance of B happening. Okay, hopefully people enjoyed that. That's a pretty interesting thing to be aware of. So that, I think, is that question done there. So I'll pause and scroll on to our next question. Okay, so scroll along there, didn't have to go too far. So we're nearing the end of the document. So we're back in this 2012 mock paper. We're getting a bit of an unusual question here. We're asked, n choose 2 is 45, find n. People be scratching their heads. It's like, I don't know how to put this into the calculator. So if you look at, I think it was the part 3 of this past paper questions on probability, I showed people the tricks on how to do combinations by hand. So you should know that something like, I'll just revise it here. It'll only take a second because I'm sure if you haven't watched the part 3 and seen this tutorial, you should go look at it. This by hand can be written out like this. You go 7 by 6 by 5 and you stop, and then you do 3 factorial on the bottom. So if that didn't make sense, go back and watch the part 3 and see where I walk through this. So type that into your calculator and then type 7 choose 3. You see they're the exact same thing, okay? I'll do another one here. 10 choose 2. All that is 10 times 9 and you stop, and then you write 2 factorial on the bottom. So that's, what's that? That's 90 divided by 2, 45. So 10 choose 2 in your calculator. It'll work out as 45. Okay. So let's do this here. I hope I haven't accidentally done what the question thing is there. I think I might have. Okay, so that's complete chance. Okay, so what's going on here? So you have to understand that you can multiply this out by hand. So in the same way, when I was doing something like say 5 choose 3, right? I'm starting out with 5, then multiplying. I see I reduce the number by 1, and then I'm multiplying all the way down to 1 basically, like a factorial. But I don't go all the way. I stop after the number of terms at the bottom. So it says 3. Then I go 3, by 2, by 1. So the same here. We're going to start multiplying down. So this here is going to be n. I'll write it here. N choose 2 is going to be equal to n multiplied by n minus 1. See, you reduce the number. Now I stop there because there's only a 2 on the bottom. It says do 2 terms, and then you go 2 by 1. And that then will be equal to the 45 they're on about in the question, right? That's going to solve the question first. So I'll hammer this out here. So this will be n squared minus n. You multiply across by the 2, you get a 90. You get a quadratic here. N squared minus n minus 90 equals 0. It should be easy factorize. N times n equals 0. Factors of 90, it's probably 10 and 9, isn't it? 10 and 9, probably a minus 10, a plus 9. So n here can be 10, or n can be minus 9. And as you've seen, by complete chance, I decided to give you the example of 10 choose 2, and it worked out as 45. So that's why, n is 10. Okay? So yeah, so that's the answer. N obviously can't be negative, so that's not possible. Okay. So yeah, that's how that works. And then I'll do another one of them just in case it came up with, like, say you were asked to get a quadratic. So n choose 3, say it was equal to something like 7, something like that. What this would look like, it'd be n times n minus 1 times n minus 2. You multiply down 3 times, and then you write 3 by 2 by 1 equals 7. And then you get a cubic there, and you might be able to solve the cubic, Grand. Hopefully people are good with that. And then obviously if you watched say the video in part 3, which you should have, you should know that n choose 1 is just n, that kind of thing. So if you were given a trick question where like n choose 1 is 7, you should know that n choose 1 is n, so n itself is 7. Okay. Hopefully that makes sense to people, because 6 choose 1, your calculator is 6, 7 choose 1 is 7, 10 choose 1 is 10, and so obviously n choose 1 is just n. Okay, so I could replace this here with n, and so then n must have been 7. 7 choose 1. Okay, hopefully people get that, and of course watch that previous really good breakdown of all those combination rules in part 3 of this tutorial series on past paper questions on probability. Right, let me pause this, get our next question. Okay, so I scrolled along there, so you'll be happy to hear I did check, because we're at the end of the document here, 131 out of 133, so I checked if there's any questions after this. There isn't, so this is the last question. So let's do this question here. So I'm really just interested in seeing, can you state whether or not 2 events are independent, and to know how to justify your answer. So pause the video and see, can you get that out there. It's a pretty easy question. So if they're independent, this formula should work. Probability of A, and it's so common this, you've really got to be able to do this kind of question. So this formula should work if they're independent. If this formula does not work, it means they are not independent. Okay, so let's check this out here. 0.3, we're given this in the question, and we're actually given these, so it's that simple. 0.7 times 0.5. You should be able to do that in your head. If you can't, I'll type it in here. It should be 0.35. It is. So then what's it saying? Oh, it's saying 0.3 is somehow equal to 0.35, which is not possible. So therefore, you just make a conclusion with 3 dots here, not independent. So what that means is what that means there is A happening changes the probability of whether B happens or not. Okay, they're dependent. Okay, great. So I'll just actually do this question here. So because of what I said earlier on, another thing, if they are independent, this thing should be equal to what? It should be straight up equal to the probability A. That is a definition of being independent. And as you've seen there just a second ago, this is used in the derivation of that formula I just showed there, where their intersection is their probability of A times probability just multiplied. So let's work out the intersection, and then we'll end the video. So A given B, this formula is always true, whether or not they're independent or not. that the intersection, when A given B, it's the intersection on top divided by the last thing mentioned, which is the B. And so when we type this in here, we get a 0.3 over a 0.5. We should be able to do that in our heads. If we're not, it's 0.6 in your calculator. And sure, look, that is different to the probability of A. 0.6 there does not equal 0.7, which is the probability of B. So that there proves as well that they're not independent. Okay, so hopefully you get that. There, if the probability of A given B does not equal the probability of A, then that means, you know, they are not independent. And as we've seen there, 0.6 does not equal the probability of A, which is 0.7. Great. But obviously, your flashcard, your learning point, if you're ever testing their independence, you just kind of start from here. Okay, so I'm waffling on a bit now. I should just end the video. Okay, so that's it. And then I'll go 2-page format here and just scroll on that there isn't any extra ones. Okay, so we've already done basically everything. We're well prepared. So hopefully you enjoyed that video and you learned the 4 parts of this video, and you learned a lot on probability and the types of questions that come up, and you're better prepared now having watched those 4 parts. So if it helped you, be sure to subscribe, leave a like and a nice comment if it helped. Okay, thanks for watching, and best of luck.